simple courses, we have a mini symposium again in the afternoon. So I encourage you all to stay for that. Also, I encourage you all to keep your video on. I think it helps the speaker to just kind of have a sense of people's facial expressions. And yeah, finally, of course, feel free to use the Slack and the GatherTown. The links you probably already saw to the lectures from the last 2 days are on YouTube. And I'll do the same thing for the lectures from today. Okay, take it away, Dan.
Thanks, Boris. Also, if you have a false and distracting background, that makes me laugh, that's great. So if I happen to look over and see something silly and interrupts the lectures, that's a win in my book. So that's encouragement to turn on your screen share. Please do. Anyway, so as we see from our course plan from last time, at the end of yesterday, we finished lecture one, according to the strikeout. So that's great. So now we're on lecture 2. Oops. And at the end of the last lecture, we discussed linear models and kernel methods. Essentially, we defined one model, which I guess I'll call a linear model, and we solved it and discussed 2 different forms of the solution. In one case, in parameter space, we solved what traditionally is called a linear regression problem, and we found optimal weights and use that to make predictions on novel test inputs. And that's this formula here. And then at the very end, perhaps it was a little quick, but I think for this group, perhaps it should be fairly familiar. We then discussed the dual sample space perspective of the same solution by plugging in those optimal weights. And we interpreted the solution as interpolation of the labels, a linear interpolation of the labels according to the kernel inverse evaluated on the training set only and the kernel involving the test input that we want to make a prediction on. Now, importantly, the features of this model expressed either as the feature functions, the phi j, or in terms of the kernel, they're fixed. So, as Sho will explain in his next lecture, or at least over the course of his 2 lectures, this kind of model is a nice model for infinite width networks, but there's a theoretical mismatch between this model and finite width networks. And I'm just alluding to these connections. Sho is going to make them more precise because we're just discussing the dynamics of in this case, this class, or we discussed the dynamics of this class of linear models. And today we're going to discuss, in fact, and the goal of this lecture is to find a different class of models where these sorts of feature functions or the sample space version of the features, the kernel, where they evolve. In other words, we're looking for what I'll call a minimal model of representation learning. Great. Any questions on this review before I go on? Perfect. So to go beyond the linear paradigm, we're going to slightly deform our linear model to get a nonlinear model, specifically what I'll call a quadratic model. So on the left, this is the model we were studying before, and now we're going to add a term that looks like this. So this model is nonlinear because it's quadratic in the weights. So here we have 2 elements of the weight matrix. They're being multiplied, and there's a various sum, and that's being used to compute the output of the model. Additionally, there's a small parameter epsilon that controls the size of this deformation, and that's sitting out in front here. And in the current context, that's some tunable parameter that you can, if you were to use this model in practice, that you could set it however you want. The validity of what we're going to discuss is going to hold in perturbation theory. So it's going to, there are going to be errors that are going to go like order epsilon squared that we're not going to compute. And in terms of how this works for deep learning, again, we'll see in some sense that the right way to set epsilon is going to be the depth to width ratio of the model of an MLP. That's something that Sho will discuss in more detail. For now, we should just think about this as some controllable parameter that's part of the definition of the model. we've also introduced, as part of this definition, what I'll call meta feature functions, these psi J1, J2s with 2 feature indices. But by definition, you should see that it's symmetric. This function is symmetric under the exchange of feature indices J1 and J2. And the factor of 1/2 that sits in front of this expression is just a conventional factor because of the double counting of our sum. And just like the feature functions before, these meta feature functions are something that you define ahead of time. You engineer it, you use your intuition about the data set, and we'll explain, we'll see after we analyze this model what the effect of this is, but it should be thought of just as a different object, but very similar to the idea of the feature functions that should be familiar. And we'll soon explain why all this is a good idea and analyze how it works. But I guess since maybe this is new, or I assume this is new, does anyone have any questions about what this definition is before I go forward?
I'm just I'm curious more about like you're writing out all the indices, but is there like a way to think about this in vector notation so that I can like think like, oh, maybe this is a quadratic form of some sorts, or like is there some easy to
isn't this a quadratic form?
Yeah, I was just wondering if like the if like psi J1, J2, it's like vectors that are these like similar to the phi j that take like a sample and turn it into a vector and that evaluate it at 2 different J1, J2 indices, I guess.
Well, so just like the phi takes an input and turns it into a vector, this is going to take an input and turn it into a matrix. And I haven't told you what goes in that matrix yet, or in some sense it's up to you. It's going to be a feature engineering type idea, and neural networks use objects like this and they do something, and we'll discuss that. Just like they do this, and we'll discuss that as well. And Andrea, I think, discussed that a tiny bit, although in slightly different notation. For our lectures, we're going to write the indices. I think the indices make things a lot clearer than hiding things using vector and matrix notation. It's much easier to, in my mind, see what's going on, and also you can always have a type of type safety as making sure that you understand the expressions, because indices have to match on both sides or be contracted and summed over. And so that's the approach that we're going to take in the rest of these lectures. Great. So moving forward.
Can I interrupt?
Yep, go ahead.
On the previous slide, I'm wondering, I think this is an abstraction of the parameters, right? It is not the case that we are specializing for one layer. It's just that we have written some arbitrary pair of parameters for the quadratic model.
Yeah, so I was starting with the linear model, which was, I explained how it's related to a zero hidden layer neural network, but the linear model is just a thing in and of itself, right? I defined the weight matrix. It contains the bias, and because phi 0 is a constant, and then there's a NF by N out matrix of weights, and it's just that's the model that we're using. That's our definition of this model. We'll explain how so yeah, you shouldn't think of these W's as coming from a particular layer of a neural network. We've left the neural network abstraction for the moment. We'll explain neural networks are going to fit into this sort of classes of models that we're analyzing. Technically, the finite width networks that we'll study are cubic models. It's simpler to study this quadratic model first to understand to understand how this representation learning is going to work. But for now, we've left the neural network abstraction behind, and we're just studying different classes of parameterized machine learning models to understand how they behave. And we started with the simplest one, which is the linear model, which is hopefully very familiar to everybody, and it's covered, in a number of books and a number of courses. So that's a familiar starting point, and it's very simple. And this is a natural jumping off point to discuss more complicated models in a sort of systematic way. Great. So a great way to familiarize ourselves with this model is to consider a small change in the model parameters and understand how the model's output changes. So all I've done here is I've Taylor expanded and written out what the derivatives are. So making this small change in the model parameters, we see that the model prediction changes in this interesting way. There's and we're considering, or there's now a quadratic dependence on the change in the model parameters, and we have some sort of interesting term in the square brackets here. So this term in the square brackets is so interesting, this derivative of the model with respect to the model parameters, that we're going to make a shorthand for it. We're going to call it phi with a superscript e, and it's going to have an index that depends on the output component I, as well as the feature index j. And as we see from this expression, it depends on the input as well as the parameter, as well as the model parameters, I should say. And so it's given by this expression here. So it's just what goes in the square bracket. This just is the linear part of the Taylor expansion of expanding the output. And we're going to call this an effective feature function. The utility of this is as follows. So the linear response of the model behaves effectively as if it has parameter dependent feature functions phi e. So that was what I showed on the last slide. By linear response, I mean I'm looking at the linear term here, and so if we make a small change, the linear response is what goes in this bracket. That's the derivative. That's the definition. So in some sense, I'm just repeating the definition, but that's important. The change, however, in the effective feature functions. So now considering this definition of these effective feature functions and making the same small change, we see that we get this expression here. This should look kind of familiar. For comparison, for the linear model, for the model output, we had this expression for the model output. And note, so the model output changes according to some linear response with the feature functions phi. Here, we see that these effective feature functions also have a linear response, and they evolve with the meta feature functions psi. So in some sense, or not in some sense, in a real sense, this quadratic model has a kind of hierarchical structure where the features evolve, the effective features evolve as if they're described by a linear model, and the model's output then evolves in a more complicated nonlinear way that I described on the previous slide. So this is also why we call them meta feature functions, that they're playing the role of that the feature functions normally play for the model output in the linear model. They're causing the feature functions to evolve. So now that we've sort of defined this model and explored it by making small changes in the parameters, the next obvious thing to do is to make large changes in the parameters. In other words, solve the model and find the optimal value of the parameters in some sort of machine learning problem. So as far as I know, supervised learning with a quadratic model doesn't have a particular name, but if it did, we'd probably all agree that the name should be quadratic regression. And the loss is now quartic in the parameters. And in general, our naive approach that we pursued at the end of the last lecture, where we're just going to take the derivative with respect to the parameters, set them equal to 0 in order to find the extremum, that is not going to work anymore. There's in general not going to be analytical solutions, and this is not a tractable practical method. In the last lecture, not only did we find an analytical solution, but people use the method that I described as a tractable practical method for doing linear regression, at least for certain sizes of features and data sets. They, in practice, have a matrix of features and they invert that matrix to get the optimal parameters. So that was both gave us our theoretical solution and a tractable practical method. That's not going to be the case here anymore.
Dan, question
Boris,
for you.
Answer for you, I hope.
Hopefully, right? So is there a simple description for this model of how big the space of minima is? Like for a linear model, it's like some linear space, in general. But here it's maybe not completely obvious. What
Linear space means
like like a hyperspace, of like W's that in principle fit the data. But here, like things are quartic, so a priori it's like a degree 3 thing maybe or something.
sure. I want to give an answer, but I'm not sure you're going to be satisfied by it.
Okay, fair enough.
So, well, what I can say is that certainly in the perturbative limit that we're going to analyze, you can solve this model, and so then you'll see what the answer is, and then you'll say, oh, there's a whatever space of features, and that's the correct, or a space of solutions, and that's the correct description. I think, but if you're asking in general, not at order, say with errors that go like epsilon squared, then probably not, or I don't know.
Okay. I was asking about both, so that's useful. Thanks.
Yeah. What I know is how to solve this model in a perturbative series in epsilon, and we can discuss that when we get there and see if that satisfies you. Great. So, right. So where were we? We were saying that. Oops. So we can't use the old method. So instead, we need something else, and we can do what the practitioners do when we're trying to optimize a function, or anyone who wants to optimize a function and you don't know how to do it analytically. A great thing you can do practically is you can put it on the computer and use gradient descent. So this will find a minimum in practice. Great. What is gradient descent? Well, gradient descent is the practical workhorse of machine learning, and it's how you optimize a function. And I hope everyone is familiar with it. I'm going to breeze through a few slides about gradient descent. Again, more to establish notations, to set up the special variants that we will need for future lectures, and just to make sure that we're all on the same page. If I go quickly and someone's confused, please stop me. I think you've certainly seen this in Andrea's lecture, and so it should, by all means, be very familiar. So gradient descent is an iterative learning algorithm. Last time when we solved the linear model, we just solved it by what I'll call direct optimization. We just took the derivative, we solved it, that was it. Here, there's an iterative algorithm. Well, this is the algorithm in general. And here, T is going to keep track of the number of steps in the iterative training process. Also here, I've introduced a hyperparameter, a training hyperparameter, eta, that's positive. And it's called the learning rate, or occasionally we'll say global learning rate. And it's going to control the size of the steps that are taken in parameter space. So we're taking steps, these are the parameters. So we're in parameter space, eta is controlling the size of this change. So eta controls the step size in parameter space. And I maybe didn't emphasize this as much as I should have in the last lecture, but one of the issues with the direct optimization solutions, either in terms of the feature space optimal parameters or in terms of the kernel method solution, is that you always have to invert some kind of matrix. And depending on whether you're over or under parameterized, the cost of doing that is, of those different things, is going to be potentially poor. Here, for gradient descent, you don't have to invert anything. You just have to compute the gradient, which scales linearly with the size of the data set. And so you just compute the gradient for each sample and then add them up. So there's computational reasons for why this is used in practice. Also, it's simple and it works. And it should continue to be very familiar. For sufficiently small eta, you can show that this algorithm, this is why it works, that the gradient descent updates are guaranteed to decrease the training loss. So here we're looking at the difference, the training loss after the t+1 step and the tth step. And I'm going to substitute in the algorithm. Then I'm going to Taylor expand in eta. And as long as we can ignore the eta squared term, then the loss is going to decrease. We have the norm of the gradient, norm squared of the gradient. Eta is positive, there's a minus sign, so we get a negative decrease in the loss. Great. And pretty typically, iterating these sorts of updates in the situations that we care about will eventually lead to at least a local minimum of the training loss. And in, let me not belabor that point. And in practice, small variants of this type of algorithm, these gradient-based algorithms, are responsible for almost all training and optimization in deep learning. I'm sure all of you know this already. As an aside of our brief aside, we need to discuss tensorial gradient descent. That is a variant where we modify the updates to include this lambda mu nu to get a more general family of learning algorithms. I think Andrea also introduced this. He used a matrix S, should be the same idea. We're actually not going to use this in our lecture here, but it's going to be very important for what Show says. So I just want to make sure that I introduce this now. Here, this lambda we'll call a learning rate tensor, and it has 2 parameter indices, so it's on parameter space. And as you can see, or as should be hopefully clear, vanilla gradient descent is a special case where we just pick the Kronecker delta or the identity matrix as this lambda, and then we would recover the gradient update from the previous slide, the gradient descent update from the previous slide. And yes, sorry, let me also, before I go on, let me also just make the point that while in the original gradient descent, we only have one global learning rate, this eta, in this tensorial version, the whole point of this is that we have the freedom to separately specify how the nth component of the gradient contributes to the update of the muth parameter, right? And that's what this mu nu connection is. And that's via this learning rate tensor. Repeating now the same analysis as the previous slide, we find for this generalized update that the loss is going to decrease again, so long as this quantity is positive, which is another way of saying that this is a positive matrix, as long as we can ignore the eta squared corrections. So for small enough eta. And for particular models and losses in question, you can then analyze this to see precisely what you need in order for this to be the case. So while gradient descent is the practical workhorse, let's now put it to theoretical use by seeing how gradient descent solves the linear model. So this model, the linear model we solved before at the end of last lecture, we're now going to do it again using gradient descent theoretically. So taking the derivative or computing the gradient with respect to the weights, we get this expression here. In principle, we took this derivative at the last lecture, but we suppressed some of the manipulations. So here I'm going slowly and being more giving more of the details. So this is just taking the derivative. Then we're going to do the sum over the Kronecker deltas. And another reason for doing this is to define an object that is the residual error. So here I'm defining this epsilon to be, I think that's actually the next line. Yeah, so the residual training error is the difference between the model prediction. This can potentially, in the future, we'll let it depend on the step. So it's the model prediction at some point and the true labels. And so the goal of training is for this residual training error to vanish. And please don't confuse this epsilon with the small parameter in the quadratic model. Here we're just talking about the linear model. There's an unfortunate overlap in notation. The small parameter in the quadratic model will never have indices. This will always have indices. Notation's hard, slides are hard. It's hard to not have collisions. So please keep that in mind. So the weights of the linear model are going to update according to this equation here. So we just took the derivative that we computed on the last slide and we plugged everything in. And now for our theoretical analysis, it's more convenient rather than understanding, well, sorry, let me take a step back. So we can analyze these weight updates, but we're going to find it's useful for a number of reasons to instead analyze how the model itself updates directly. So rather than focusing on the optimal parameters in some sense, or in a real sense, we can just pass directly to the dual sample space and consider how the model updates itself. So here, what I've done is I've taken the model and I've Taylor expanded it after making an update. I haven't even put in what the update is. And in general, there's many terms, but for a linear model, it truncates because the model is linear in the parameters. And now we can plug in what this update is. And now we can rearrange a bit. And oops. So sorry, we can plug in what the derivative of the weights are, and then rearranging a bit. And then we notice that something really nice has happened here, right? Before, by plugging in this update, we get an inner product of these two feature functions, and we know that that's given by the kernel. So we get this very nice expression at the end after looking at how the model evolves. Also, I meant to comment on this before we moved on, but I didn't note that. So let me just go back and make some more comments about this equation. Note that for these weight updates, what this equation is telling us is that the feature function, so for a particular input x alpha, the features that we compute phi j then can contribute to the way in which the weight updates. The weight connects the features phi j to the output of the ith component. So naturally, the way the update works is that the features phi j and then the prediction error on the ith component combine to update the weights wij. So that's kind of a parameter space description of how these updates work. Note now for the well, yeah, sorry. I guess let me make this point before saying what the bullet point says. So note here as well that for the sample space description, now we have a residual training error on an element of our training set, x alpha, and the update then tells us to an arbitrary example, say an arbitrary input x delta from either the training or test set. The way that is going, the contribution to the change in the prediction to that update depends on the training error in an element of the training set, and then it's mediated by the kernel component that connects that training element, that element of the training set to the element x, to the input x delta. And this should be intuitive as well because there's some prediction on x alpha, and the kernel is a measure of similarity between two inputs using our feature functions. And so as inputs are more similar, this element will be larger, and so prediction error on x alpha should also help us correct a prediction error on x delta. So this is how function approximation is working. This is how we're able to generalize by having components like this. So that's a way to think about the analysis of the structure of this update. And now moving on, one important point, this is a point I emphasized at the beginning of this lecture when discussing linear models. It's also true for gradient descent that K is fixed, the kernel is fixed. Here we see that it's generating the dynamics of the model. This is similar, for those of you who have studied physics, to the way the Hamiltonian generates the dynamics of a system. And also, another way of interpreting the words I said before about the residual training error alpha affecting delta and so forth is that the kernel is, in this perspective, a type of metric on sample space. And finally, I guess I'm kind of belaboring this now, but the training errors, the residual training errors, you can think of as sourcing the updates for general inputs, delta from a general data set. Great.
Dan?
Yep.
Could you elaborate on how it's similar to how a Hamiltonian generates the dynamics in physics?
No, not really. I don't want to go down that direction. I guess the main point is that the evolution operator is normally like something like e to the Hamiltonian times time, and there's some depending on what type of physics we're talking about. But if you take the derivative of that, right? This is a difference equation. If you think about it in continuous time, the update is
Right.
going to be a derivative with respect to time is going to be proportional to the Hamiltonian. So
Okay, I see.
same sort of thing that's happening here. But beyond that detail, I don't want to elaborate further. So now let's solve this. We have this simple linear difference equation to solve, and we're going to solve this. We're not going to take any continuous limit, because in practice, the steps that we take when we put gradient descent on our computer, they're not continuous. They're discrete. So let's solve the linear difference equation. It's just as easy to solve ODEs as it is to solve difference equations. So first, we're going to restrict to the training set, and we get a first order homogeneous linear difference equation. And then we're going to subtract from both sides the labels. So that lets us rewrite this equation as a simple equation for the residual training error. And I've just now taken that equation to the next slide because, again, doing algebra on slides is difficult, but we're going to rewrite these dynamics. I just pulled the training error out, and we see that the update is just a constant matrix. Remember, the kernel is constant, the learning rate is constant. This is just the identity matrix. So we have a constant matrix times the residual training error. So this is repeated multiplication by a constant matrix. I'm going to define the step evolution operator. I might accidentally call this a propagator. If you know what that is, it's a propagator. I'm going to try to call it a step evolution operator. So each step we multiply by this constant matrix. So after t steps, this u of t evolves us for t steps, and it's just taking this matrix to the power t. And so I've written it out here what this definition is. And the solution is just this repeated multiplication by this matrix. And that should be clear, or hopefully is familiar, repeated multiplication by a matrix leads to exponential behavior in the number of times that you multiply. And so we expect that as the number of steps becomes large, then the operator u of t is going to vanish, such that the residual training error vanishes and the model predicts the true outputs on the training set. The model learns the training examples. And this will be true for positive definite kernels and sufficiently small learning rates. And we can, the details of that are completely straightforward, but this should be pretty intuitive, I think. So having done that, we still have to solve the difference equation for the test error. So now we know what the residual training error is. We just solved it on the last slide. And so this is a known function of step, and we can iterate this equation. So I just iterated this equation, and we get a sum over these residuals. And what we actually care about is the end of training, not some arbitrary time t. So we can take the limit t to infinity. Note, I just want to emphasize this is a theoretical tool, but actually in practice, you don't actually have to run the algorithm for an infinite number of times. The solution converges exponentially. So very quickly, according to the time constant of the exponential, you're going to be in a regime where the solution has effectively converged. Taking the limit of t going to infinity here is just a convenient way to analyze the minimum. But in practice, you don't need to run for an infinite number of steps. Obviously, that would be unphysical. So now I'm just plugging in a solution from our last slide. And again, plugging in the solution from the last slide, or I plugged in first propagator and then for its definition. And so we recognize here that we just have a geometric sum. Hopefully geometric sums are familiar. Here we have a matrix version of it, but this is it's the same idea. If you have a sum of x to the s from s equals 0 to infinity, the answer is 1 over 1 minus x. And similarly here, we get 1 over 1 minus this matrix using the matrix inverse. And so it's just a matrix version of that statement. And simplifying further, we can deal with the subtraction and deal with this inverse. In this case, we get a simple expression that hopefully should be somewhat familiar given the analysis we did last time and the discussion at the beginning of this lecture. in other words, comparing this gradient descent solution to the direct optimization solution from before, these are nearly identical. In particular, if this solution does depend on the initial value of the weights, the model weights, and if they're initialized to 0, then these solutions would exactly match. Remember, the residual training error is z minus y, and so this evaluated on so when this vanishes, then there's a minus sign here, and these expressions are the same. So this, before moving on, this issue of the initial version of the weights comes from the fact that we were slightly not careful when we were dealing with the matrix inversions in the direct optimization solution. And in principle, we would have to regularize that sort of inversion depending on which regime we're in. And so there's a slight ambiguity about that. I don't think it's particularly important. One way to think about fixing this is by adding an L2 regularization to this model and analyzing it. But that's where this comes from. But aside from that, these models have an algorithm independence. Excuse me. So what I mean by that is, regardless, there's a unique prediction, a unique minimum for the model predictions up to this small ambiguity, and regardless of what learning algorithm you use, what other version of gradient descent you used, or if you had picked a different learning rate, none of those details matters, because it's the gradient, any version of gradient descent you use, for instance. So any choice of learning algorithm, as you might imagine, when we use these sorts of optimization methods for deep learning, choices of learning algorithms and learning hyperparameters affect the predictions on the training set all the time. And here, that's not the case. For these models, that doesn't show up. So it doesn't depend on the details of learning algorithm. And importantly, again, the features are fixed and don't evolve. So even though, regardless of using this other method of solution, we still need to consider our other quadratic model in order to see some non-trivial feature evolution. So that's sort of our warm-up of understanding how to analyze gradient descent theoretically, and now we're going to move back to the quadratic model.
Do you need to assume anything on epsilon, smoothness or something?
Which epsilon?
In the previous slide.
I don't.
Yes.
For the difference between the model predictions and the labels.
Yes. Because I see it as kernel approximation. It feels like you need to assume some smoothness or low oscillations to get exponential convergence.
Well, why do you say kernel approximation? There's no approximations here.
Maybe, okay. It looks like approximating using kernels.
Approximating what?
For example, approximating the error. It looks like you take samples from a domain, scattered samples, and then you take a discrete kernel or something like you take the kernel in those points, and then you approximate the error.
I'm not sure I'm following. So we're not taking a neural network and approximating anything. We've just solved. We've just done linear regression, right? And we've just inserted.
Yes, I see. Okay.
Maybe it's useful to say that everything is finite dimensional, so there's no smoothness on epsilon.
Yeah, I mean, another way. Thanks. I was going to say, we have a finite training set. You can imagine connecting it however you want, so you can make it smooth if you want to. I haven't talked about a data distribution, and yeah, there's nothing crazy in the data distribution, but I think this is generally, this works in practice. This is a safe assumption of practice. Okay. These solutions are going to work for, like, MNIST or ImageNet, or I mean, linear models are not a good model, but for the data set that you care about for machine learning purposes and for statistical in statistics, this sort of thing works. I think there's another question.
Yeah, so is the kernel always invertible though? I mean, because like if we have linear regression and stick to the parameter space, we may not be invertible, right?
Right. So I glossed over that a bit, but because I don't think I don't think it's worth belaboring here. I mean, that's why we have these slight difference in the solutions here. So the regime we're going to care about is the over-parameterized regime, in which case the kernel is invertible, but we have this slight ambiguity. So if we do gradient descent, then everything's fine, and you just get the solution here.
And that's basically because we moved to the output space. Is that correct?
That's one way of thinking about it. I mean, another better thing you can do is define how these inversions work. So you can add an L2 regularization, everything is then invertible. And then, so one way of thinking about what I'm doing is I did that, but then I took the limit where the regulator goes to 0, and that picks out a particular solution. And that's this one here.
Okay, thanks.
This is not going to matter for the, I mean, this is true. That's why I'm not hiding it, but it's not going to matter for the points that I want to make here. In this case, well, maybe I can just say for the quadratic regression problem that I want to solve, we're going to use gradient descent, and we're going to be in the over-parameterized regime. So kernels are invertible. Okay, other questions or let me just check time. Okay, great. Okay, so we had this slide already. It's just a repeat, but the point is, now that we know what gradient descent is, we're going to analyze this quadratic regression problem using gradient descent. So, and here I've just, okay, so here at the bottom, I've taken the small change in the parameters and small change in these effective feature functions. We derived these equations earlier. I'm just reprinting them here. Up here, I don't think we discussed this, but it's natural if you take the derivative of the loss with respect to the weights. So if you take that derivative here, then it's easy to see using our definition of these effective feature functions that the weights now evolve, but rather than the fixed features, we have the effective features here. So the way in which the weights evolve care about these parameter dependent features and still the residual training error. So that's an exciting difference. And we see that under gradient descent, not only is the model is nonlinear, has some sort of complicated dynamics, and the features are evolving. So the plan for the rest of this lecture, and I'll try to go through it and explain things carefully, is to analyze the gradient descent dynamics of this model. And then I think the details of that are kind of important for understanding and getting a feel for how this model works. And then more importantly, we want to understand the aspects of the solution that make this different from the linear model and understand the mechanism behind which features, well, first by analyzing the dynamics, we'll understand the mechanism by which the features are evolving. And then by analyzing the solution, we'll see how evolving features affects the predictions and how we can interpret this as representation learning. So first, let's look at the update to the model prediction. So here, this is the expression that we have for the, it's a quadratic model. So this truncates and it evolves with the effective features here as we discussed. And so now we have to plug in for the gradient descent update, which I've done here. Then I believe in this line, I've now just rearranged using commutations. Everything's commutative. I mean, I've just rearranged things simply in order to highlight two things. First, note that the evolution of the model, before it was linear in the residual training error, now it's nonlinear. So it's quadratic in the residual training error. And because the residual training error goes like z squared, this is a nonlinear difference, a nonlinear difference equation in Z. Note also that there's a part that's linear in the learning rate and also a part that's quadratic in the learning rate. Finally, I've identified two interesting objects in square brackets that we're going to take the next 2 slides in order to discuss and in order to simplify this a bit. Well, I would say both of these things should be very suggestive, but one of them should be in particular suggestive. So again, by analyzing the dynamics of the model output, we're passing to this dual sample space picture. So analogous to the effective feature functions, we're going to define an effective kernel. Just like the original kernel that we defined, the fixed kernel that we defined last lecture, here we have an inner product in feature space, and it measures a parameter dependent similarity between 2 inputs. But now instead of measuring that similarity using the fixed feature functions, it does it using these parameter dependent feature functions. Finally, since these feature functions carry an output index, so too does the kernel. So there's an I here and there's an I here, and so the kernel for each output component for each output component, there's now a different parameter dependent kernel. The reason I write I twice is just for when in future lecture, when Shou is going to generalize this a bit, we'll need to have different output indices for an analogous object. But here, there's no in principle reason why you need to write I twice, but it does need to carry a output index. Okay, sorry. I hope that's clear. So as a second aside, so perhaps going back to, so we discussed this square bracket, the term in this square brackets. Now we're going to discuss the term in this square brackets here. So that square bracket suggests that there's an important object worth defining. That object we're going to call the meta kernel. It's a parameter independent tensor defined entirely in terms of the fixed feature functions, the phi j without the e, and the meta kernel, the meta feature functions, the psi j1, j2, that are part of the definition of a model. And one way to interpret this is that for a fixed input, x delta 0, then the meta kernel computes a feature space inner product between 2 inputs, x delta 1 and x delta 2. Note, the meta kernel is symmetric in these last 2 sample indices, but the first index is privileged because that's where the psi goes. And due to the inclusion of our small parameter in the definition, we should think of mu as being parametrically small as well. And so that's the explanation for going from this line to this line. So we can define mu to be parameter independent using these fixed feature functions and meta feature functions. But then an expression that has the effective feature functions is equivalent to this up to errors that go like epsilon squared. So with those 2 definitions in mind and their interpretations, now we can make some substitutions. So substituting in for the effective kernel here, and then substituting in for the meta kernel here, and then leaving orders of epsilon squared, we get a pretty simple expression for the evolution of a model. So this is a coupled nonlinear difference equation. It's nonlinear, as I explained before, because of the epsilon squared goes like z squared. Note importantly that the meta kernel doesn't depend on the parameters up to errors that are epsilon squared. And it's coupled because the kernel is now evolving. And so we also need to understand that it's coupled to the dynamics of the kernel. And so in order to solve these dynamics, we need to now work out a dynamical equation for the kernel also. And again, finally, please don't confuse the residual training error, which are decorated with all sorts of indices and with a step argument with this epsilon that defines the small parameter in the definition of the model. And going forward, there might be one more slide where I include these plus order epsilon squareds, but going forward, I'm going to drop it for the most part. So we won't in general see it. And when you see epsilons, it means the residual training error. So in order to continue analyzing these dynamics, we need to find an effective equation that describes the effective kernel dynamics. So starting from our effective feature functions, one thing we should do first is plug in the gradient descent update and then reorganize. And okay, so sorry, epsilon appears here. Very soon, epsilon won't appear. So we might need to translate the statement that I made on the last slide up forward a few slides. So please bear with me for that. So now what I've done is I've taken this equation and I've squared it for different inputs. So taking this equation for delta 1, an input x delta 1, taking this equation for an input x delta 2, and then multiplying on both sides, or taking the product of those equations, I should say, and summing over the feature index j, I get this expression down here on the bottom. And the reason, so there's 2 terms on the right-hand side here. I have 3 terms here, so I'm dropping the square of this term because it's order epsilon squared. So that's why we see there's 3 terms here. Moreover, because this expression already contains epsilons, we can replace these effective feature functions with the fixed feature functions. And now the definitions that we made on the previous slides should come in handy. So we can, instead of, let me, just so it's clear, so this is going to be an effective kernel, this is going to be an effective kernel, and these square brackets give us meta feature functions. And making those substitutions, we have a dynamical equation for the kernel. So this is a linear difference equation with the meta kernel playing the role that the kernel played for the evolution of the linear model output, model output. And just as the fixed kernel based on the feature functions generated the dynamics of the linear model, here the fixed meta kernel based on the meta feature functions is going to generate the dynamics of the kernel. And it's sourced in the same way by a linear term in the model output, or in the residual training error. Okay. So we have 2 equations now that are coupled. The model predictions evolve with this equation. The effective kernel evolves with this equation. And so these joint updates are coupled difference equations. The first is nonlinear in the training error. And the second is a linear equation. And so we're going to solve these equations in closed form to leading order in epsilon, non-trivial leading order in epsilon using perturbation theory. In order to do this, it's useful to decompose the model into a free and interacting parts. Or in other words, we want to separate out the part that solves the linear model dynamics from before. This is just the linear dynamics from before, where I've written Z with a superscript F. And I'm just reminding you, for some reason, of what the residual training error looks like. So this ZF solves this equation, and we already know what that solution is. Therefore, we know that this interacting part of the model output is going to be the order epsilon, since as we take the epsilon goes to 0 limit, we're just going to get the linear model back. As we take this limit, the deformation of the quadratic model vanishes, we get a linear model, and then we know that the linear model solves this equation, so we should expect that this new part is going to scale like order epsilon. So let's solve the effective kernel evolution equation first. This is very similar to what we did at the beginning of the lecture. First, I'm going to substitute in for the residual training error, and note that because well, sorry. So first, now is when I'm going to drop the errors going forward. So sorry for saying that sooner. And now note that we can drop the interacting part of the model output because mu is proportional to epsilon already. And so that is going to be something subleading. And so we can rewrite this equation such that it only depends on the linear part of the residual training error, which we already computed. So all I'm doing now is plugging in the solution from before. And so before we computed the geometric sum to infinity. In this case, we actually need to know what the kernel is at different steps t. So I've defined a helper function a, which is just doing a geometric sum, but rather than taking t to infinity, now it's the version of the geometric sum where t is finite. So this hopefully is familiar in its non-matrix form. It's the same thing with the matrix, you just have to get the indices right. And in the end, what we see is that so this a has some explicit expression. First of all, when a is 0, the residual training error cancels, and so this expression is 0, which means, sorry, my slides are not going backwards. So that means that the kernel is just given by its initial value. And secondly, as t goes to infinity, this is going to 0. So at any step, basically the amount that the kernel has evolved is given by the difference between the initial prediction error and the current prediction error. And so this is great. We're seeing that the kernel is evolving, which is what we set out to find, and we're understanding how it's evolving. So now that we've done that, let's solve the interacting part of the model. And okay, so I have, it looks like 3 minutes left. Maybe we started a few minutes late. Is it all right if I bleed maybe 5 or 10 minutes into the question and answer section, Boris, or I can skip some of the details here and post them later and people can do them on their own?
I think that's fine. 5-10 minutes is fine.
Okay, great. So there's some technical details here. I think if I just gave you the solution, it'd be worse. So I'm going to spend a few minutes going through the details. I think if this is probably going to feel fast. So if it is too fast, then please either ask me or show about it in the Slack, or feel free to look at the slides, and we can cover this in more detail. So anyway, we want to solve this equation here, where I have to define what's going on here. First of all, to get this equation, we took the nonlinear model equation, and we used the fact that the free part satisfies the free dynamics. So it's not on the slides, but it's some simple manipulations that you should be able to do. And in doing this rearrangement, we've defined what I'll call a damping force, this F here, that depends on the difference between the current value of the kernel and its initial value, and depends linearly on the residual training error plus an additional nonlinear term. And so what's important about this now is that we know this is just some known function of step t. There's no other dynamics to solve. We've solved all the dynamics. So this is just some known function of t. And so we just have to solve an equation with a known function of t. In other words, first restricting to the training set, we're going to get a first order inhomogeneous linear difference equation where the damping force is ruining the inhomogeneity, or is ruining the homogeneity. So this is very similar to the equation that we had before for the linear model, plus there's this arbitrary, or not arbitrary, but known complicated function of step that we have to take into account. And probably everyone has more experience with ODEs than with difference equations, but they behave very similarly. So when you have this sort of linear equation with a forcing function, you can formally solve it as a convolution. So here we have a convolution of the forcing function with the propagator, and a sum over the steps. And so rather than deriving this, you can take this, or you can check that this is true by taking this and plugging it back in here using the definition of F from the last slide. These slides will be posted if you want to do this in detail, and see that the solution is going to satisfy these dynamics. So given that formal solution, now we need to analyze things for general inputs. And again, now this is a known function of step. Since we solved the dynamics on the training set, this is a known function of step. So we just have an entirely known function of step, and we can iterate these dynamics. And so iterating these dynamics, we see that the solution is given by another sum over these terms here. And after some more manipulations, probably best done in the privacy of your own notebook, you can get a slightly less formal solution. To do this, you would plug in the convolutional solution here that we had on the last slide. There's two sums, and you want to reverse the order of the sums and do some other manipulations. It's something fancy, but the point of doing that is that this is a much nicer form to analyze. So one point as a quick sanity check to make sure that this makes sense, if you plug in for an input in the training set, so take an input delta to be alpha tilde from the training set, then this general expression is going to reduce to an identity on Z alpha. In particular, this is going to give you a Kronecker delta. This term is going to cancel. This is going to give you a Kronecker delta, and this part will equal that part. So at least that's a quick sanity check that this expression makes sense. So now there's going to be two more parts before we understand an answer. First, we will analyze this term, and then we're going to analyze this sum over the forcing function. So ultimately, again, what we care about is at the end of training. Before, we discussed how the propagator decays exponentially with step, as long as the learning rate is small enough. And then for the training inputs, the interacting part of the training input output, they're going to exponentially converge. To see why this holds, remember it was a convolution of f with the it's a convolution of f with u with the propagator, and so f also decays exponentially since its leading behavior is proportional to the residual training error, which we solved and we know decays exponentially. So putting this all together, this is going to mean that this additional part of the residual training error, this zi, is going to converge exponentially to 0, although slightly slower than the free solution did. So there's some linear dependence on step out here, and there's a different constant up here. I probably should have written eta in this exponential, or I should have written eta in this exponential. So what we've shown is that, first of all, the overall training algorithm converges, great. So going to this more complicated model, we're still learning all the examples in the training set. And secondly, note that this correction part is converging to 0, because for the linear free part, we already know that it makes perfect predictions at the end of training. So we can't modify that. So we must have that this additional part on the training set is going to decay to 0. And further, we've also seen that while there's exponential decay, it's slightly slower. So this model takes a slightly longer time to converge, or sorry, slightly longer number of steps to converge than the linear model did. And although I haven't connected quadratic models to neural networks, I mean, I've explained that the way in which they're related. I just want to make an aside that you can use the same sort of analysis to show that finite width networks converge, learn their training set and converge to a zero error minimum for solutions for realistic MLPs. So having gone on that brief aside, we now know that at the end of training, this term is going to vanish. So the solution at the end of training is just going to depend on summing over this forcing function. And essentially, it's just one more infinite sum to perform. We know that the kernel solution has a part that depends on the residual training error. So we basically have to compute sums that are quadratic in the residual training error. I'm going to go quickly here. So this is just showing what that looks like. The important point is that we need to compute a sum like this. And again, it's a matrix version of a geometric sum. The catch here is that there's not going to be a simple way of writing this inverse. Instead, we're going to introduce a new tensor that we'll call an inverting tensor, x2, that has 4 sample indices, and that satisfies implicitly this equation here. This is similar if this was just a scalar, so like 1 minus x to the s, and this was 1 minus y to the s, then computing that geometric sum, you would get that it's equal to its inverse, or you would get that it's equal to 1 over x plus y minus x times y. So the inverse of that's what this equation is saying, but in matrix form. So it's just a matrix generalization of that. And so with this in hand, we can then assemble all the pieces together. Let me just check it. Okay, great. So assembling all the pieces together, we're going to find a solution. And you just have to go and work through those sums and plug in with the right coefficients, and you get this solution here. So I know I'm over. I think I have just 3 or 4 more slides, and this is kind of the whole point of the analysis. So I hope it's all right to continue. Here we have the linear model kernel method solution from before, and these terms are new. These terms, first of all, well, I'm going to explain, I guess, I'll explain more in detail in the next slides, but while we're still here, we see that these terms depend on the meta-kernels and some combination of the kernels. They're also quadratic in the residual training error. And I've introduced what I called algorithmic projectors, ZA and ZB, that involve this inverting tensor and some combination of the kernels. And so a couple of things to notice. First of all, if we took beta as a test index, as a test sample, but if we took it from the training set, then this would give a delta function, and this term would vanish, this term would vanish, and we would still recover that we get perfect prediction on the training set. However, on the test set, we're clearly getting very different predictions than we did for the linear model. This is clearly something different. This is the linear model solution, and in general, this is going to be a very different type of prediction. So let's, now that we've done that, I just want to take the final moment of your time to explain what sort of predictions that is. So first of all, in analogy to kernel methods, this is a dual form of the quadratic model solution. And so we're going to call it a nearly kernel machine or nearly kernel methods. Nearly because, again, this is a small deformation of the linear model that incorporates these interactions between the weights. As I think, or as hopefully is clear, or maybe I can emphasize. So first of all, notice, for instance, that this algorithmic projector depends on the learning rate eta. So unlike kernel methods, the solution here does depend on the details of the learning algorithm. And I don't have time to show it on the slides, but if you had taken the derivative of the loss, set it equal to 0. So I said that there was no general way to solve that, but if you had expanded in epsilon and used perturbation theory, you can actually solve that direct optimization equation in analogy to the way that we solved, or very similar to how we solved the linear model at the end of the previous lecture, and we'd have found different algorithmic projectors. And moreover, in the ODE limit, where we take eta to 0, we get different algorithmic projectors. So sorry, those should be Ks. So the point here is that in this algorithm, the predictions that you get on the training set, that you get on the training set are you learn the true label, so you learn the full training set, but the predictions that you make on the test set depend on the details of how you optimize the model in this sort of characteristic way. So we have 2 ways of thinking about the solution. I think I sort of said this already, but there's one, you can find the optimal parameters. I didn't explain how to do that, but you can, or when you put it on your computer and you optimize using gradient descent, you'll find the optimal parameters, and you can use those to make predictions, throwing away the training set, or you can use the formula on the previous slide in which the features and meta features or the model parameters don't appear, and you have that formula tells you how to make the predictions that the model would make using the optimal parameters. So this is the dual presentation, similar to the linear models and kernel methods duality. And as I said, the predictions here are made by direct comparisons in the nearly kernel formula by direct comparisons on the training set. There's the linear piece proportional to the kernel piece that's linearly proportional to labels. And now we're not just doing linear interpolation. There's a new quadratic piece that depends quadratically on the labels. And I think there's just 2 more slides of content. The first, I just want to emphasize that these algorithmic projectors are really interesting, I think. The predictions, first of all, if you analyzed the evolution by direct optimization versus gradient descent with a different learning rate, all the predictions take a kind of universal form where all the dependence of the algorithm, the learning algorithm for the optimal parameters is encoded in these projectors. And so what's interesting is they give a theoretical means of really isolating the inductive bias of the training algorithm versus the other inductive biases of the model. For instance, the definition of the model or the properties of the data set. This is how let me say that more clearly. What I mean is that this lets you counterfactually ask how different learning algorithms lead to different predictions for the same model and same data set. And I think one thing I really want to emphasize is this is like the sample space dual of a learning algorithm. Just as we have feature functions or we have the kernel and there's this duality between them, now the learning algorithm itself, the gradient descent updates, clearly operate on parameter space. And then after this analysis, we get these nice algorithm projectors that have sample indices only. And in principle, this even gives us a means of what you might call inverse algorithm design. You would engineer a desired functional form for these projectors and then try and determine the parameter space training algorithm that leads to projectors that have those desired form. And this has the potential to unlock some kind of deeper understanding of the relationship between the inductive bias of the training algorithm and the other inductive biases in the model. One point of caution, of course, is just as it's hard to figure out the phi's if you know a kernel going in the other direction, it's probably hard to figure out the learning algorithm if you only know the projectors. But on the other hand, if you just want to work on this dual sample space, then you can pick whatever projectors you want and use that to make predictions. And that's a formula without having to worry about the particular details of the learning algorithm. So I think there's just 2 more quick things I want to say. So first, I'm going to pick, for simplicity and so that it fits in the slide, I'm going to pretend that we solve the model using this direct optimization. So the formula for the kernel is a little bit simpler. And one thing that I want to point out is you can now define a trained kernel that averages between the fixed kernel and the dynamical effective kernel. You don't have to worry about this notation. We're never going to use it again. The real point is that using this and expanding with this definition, you can show that the nearly kernel prediction formula of this quadratic model can be compressed into this form, which is the exact form of the kernel prediction, but with the benefit of incorporating the trained kernel, the non-trivial feature evolution. And so this is a model that exhibits an evolving kernel, evolving feature functions that learn from the data, and you can analyze this mechanism and understand it in detail, and understand how the selection of the size, the meta feature functions, cause the feature functions to evolve and how they're able to learn from the data. And so in this simple minimal model of representation learning, all this intricacies of how representation learning works is contained, but can be analyzed completely. And I think this is the last slide of content. I just want to make one final point, which is that you can also analyze this in parameter space and find the optimal parameters for this model and make predictions. And the comment that I want to make is, in the same way as we decompose the model output, you can also decompose the optimal parameters as a free part and an interacting part, where these free parts are the optimal parameters from the linear model. And the point that I want to make is that these interacting part of the weights are order epsilon, from the same argument that I gave before, that as we take epsilon to 0, we should just recover the linear model. And these are ruining the fine tuning of the perhaps overfit linear model, as these WIs, first of all, are small. So if these guys, the free parts, have some intricate fine tunings, then we're going to ruin them by adding some small numbers to them. And secondly, they're ruined and they're constrained. They can't overfit because they're constrained by a function that doesn't depend on the data that we defined before training. So the point is just that this is assuming that you made good choices about the meta feature functions, just like assuming you made good choices about your feature functions is necessary in order to lead to a good linear model output. Assuming you made good choices about these meta feature functions, we might expect that the quadratic model will overfit less and generalize better than the linear model, because they have this sort of constraints that is ruining the fine tuning. And so I just wanted to give this as a reason for why this sort of model you might think of in a traditional way as regularizing overfitting, as an explanation of why representation learning can actually help you generalize better. And that's all I have for today. Thank you for allowing me to go over by 15 minutes.
Okay, thanks very much, Dan. Let's thank Dan for what I think was a very interesting lecture. I think this nearly kernel stuff is like, needs to be investigated more, but it's like very promising for understanding how feature learning can happen, at least in some models.
Thanks.
Yes.
And I just want to say that this is how it works in deep MLPs and probably in many deep learning models. You have to extend to a quadratic model, so there's a little more details, but it's essentially this sort of process. And assuming we have enough time to get through everything, in lecture 5, we can give the formula for the predictions of finite width networks at the end of training, and it will look very similar and have a lot of the same properties that I discussed in the model today. And so that's what we're building towards. This is not just, this is a toy model that's interesting to investigate in and of itself, and may be useful in and of itself, but also the point is that it's going to provide intuition for how the real thing actually works.
Right. Okay, well, let's thank Dan again.
Thanks.
Looks like there's lots of questions, so assuming you're willing to stick around.
I'm willing to stick around.
Take the questions, and otherwise, the next lecture is in like 13 minutes, so there's plenty of time.
Great. And if we run out of time, either we can do the Slack or maybe, since we don't have TA sessions, I don't know, Boris, if you assigned all the extra time, but I'm willing to show up. I'm willing to figure out a time to show up and answer questions if people still have questions.
Yeah, you should coordinate that on Slack. There's this symposium tonight, but if people want to like set up a Zoom with you or whatever, and you're willing to do that, that sounds great.
Okay, great. But maybe we can get through them all now.
All right, I guess.
Go ahead.
Yeah, I guess my question was earlier when you added up like many terms in the geometric series, or in other times we kind of ignored the O of epsilon squared. But from like my naive perspective, that seems a little dangerous unless we have like shrinking bounds on all the stuff beyond the epsilon squared. You might add like order 1 over epsilon squared many terms. So is there some more complexity to that I'm not seeing?
The sum converges.
The sum of the stuff beyond the it's like tied to the epsilon squareds converges.
Oh, the sum I did converged, and then the error, I see that.
Like when you add infinitely many epsilon squared error terms, it can still blow up, or?
Well, so first of all, in this model, I can make epsilon as small as I want, theoretically. In practice, obviously, that's not a useful model, but you can take the limit where epsilon is parametrically smaller than everything. So for the analysis I did, we don't have to worry about that. You might similarly raise an objection for the linear analysis, right? And of course, now we did the quadratic part, and there's no problem. So there's a number of ways of seeing this. First of all, you can go to the next order and analyze the next term and see that it's not a problem. What you're going to find is similar exponential decay of these terms are going to converge. So I don't think there's a problem. You can also put it on a computer and see, and it's a good model for what actually happens.
Thanks.
Does everyone, I don't know how this works. Everyone with their hands up, they want to be called on, or does it work for people to just ask questions, or what? I guess Gadi is next on. I have a line of questions on my top row, so I'll just call. But I guess put your hand down when you're done with your question, please.
Yeah, thanks. So regarding, I think, your last point about the regularization. So I'm not sure how it fits in with say Misha Belkin's content, because that would kind of suggest that kernel methods have a certain degree of tendency to overfit, and then this kind of fixes some of that. So
Yep.
I'm a bit confused. Is that kind of fair to say?
Well, I'm not sure what the, I mean, kernel methods. Let me. I think I can answer your question. So first of all, I didn't. A couple ways of thinking about this. First of all, in the overparameterized regime, kernel methods might work well, and in fact, we'll talk about in the infinite width limit, or will talk about in. I don't see it. Oh yeah, in this lecture, he'll talk about how generalization works in infinite networks. I don't know if it's similar to what Misha is going to talk about, but clearly infinite width networks do something well. And so there's understanding how good is the linear model. Then there's the question of after the linear model. So if we take the infinite width limit and relax to finite width, is that adding something else? Doesn't make it better. So this is just saying it makes it better. Now that's the first part of my answer. The second part is that
can I just comment on that, because I know of some like empirical results from guys at Google that show that for MLPs on image classification, NNGPs do better than finite networks, as I recall.
Yeah, but that paper, I'm not sure if it appropriately studied. I mean, you have to be careful because I didn't say what epsilon is here, right? So we need to make sure that we understand how this corresponds to the actual details of the MLPs. Well, I'm not talking directly about MLPs here. So you have to make sure that the situation that they studied. So in particular, the situations that we're interested in, are in the regime where the aspect ratio is in a certain limit. So if your aspect ratio is too big, as I discussed in my first lecture, then things are not going to behave well. So I'm aware of that paper, but I don't think that they were careful about.
You think they have like too many layers?
I don't remember the details. I don't remember the detail. Yeah, probably that's likely. Or I mean, I think it's in general. I mean, I would dispute the fact that MLPs are that representation learning is not useful for MLPs. However, it still could be true. That still could be an empirical fact, and everything that I said could be fine. The issue is how the size are defined, right? I said the size have to be useful. If your size are not useful, then you're not going to do better. And for MLPs, as we'll talk about, the thighs and the size, the features and the meta features, they're given by the definition, the microscopic definition of the model. So it could be the case that for CovNets, the size are good, and for MLPs, the size are bad. I mean, if that empirical result is in the right regime and that's true, then that would be the case, and that would be something to understand. But the analysis that we do, I mean, is in the same way that the infinite width analysis is accurate up to errors that are 1 over n, our analysis is accurate up to errors that are 1 over n squared, or really L squared over n squared. So I mean, this is just what neural networks, or I haven't proved it yet over the course of the lectures, hopefully though we will, that this is what neural networks are doing. And so either it helps or it doesn't, and that depends on the definition of these feature functions. One point I wanted to make though on this slide, so in my analysis here, I didn't talk about whether we're in overparameterized or underparameterized regime, and you could do it either way. In the sample space, it's better to be overparameterized, but you could also add a regulator. You can still do the same analysis. And the point I wanted to make here is an intuitive understanding of, so for instance, if you're in this regime where things tend to overfit, for instance, if you're doing polynomial regression and you have a polynomial basis, there's a typical picture of the function that weaves through all the points, right? And that the classical understanding of that is that the coefficients of your polynomial regression are going to be very fine-tuned. So the point that I was making is that is that that's a linear regression with a set of with the phi's that are chosen from a polynomial basis. And this is a way of understanding of how this model would mess that up, right? We're picking something ahead of time and it's messing up those fine tunings. So you can't have those sort of fine tunings in that classical example. So for me, at least, that's helpful because, there's, I guess maybe a better way of putting it is that there's perhaps two components of understanding generalization. One is that over-parameterized models might do things that are different than under-parameterized models or models that are equal. And that's something worth understanding. And secondly is learning features from the data good or bad? And here's a way of understanding why it's good.
Okay, I have lots of more questions, but I'll let other people ask.
Okay.
Thanks.
Okay,
thanks.
Frederick is next on my, thank you. Frederick is next on my screen, I think.
Yeah, I'm just wondering if I can get this untangled, that you talk of algorithm independence, but in a sense, I mean, I don't really understand what more freedom you have in terms of algorithms, because if you change your parameterization, or if you change from, let's say, SGD to Atom or something, then in a sense, this changes your kernel, right?
No,
So
it doesn't. It doesn't change the kernel.
The kernel is dependent on the parameterization choice, in a sense.
I mean, so it depends on how you're going to separate the parts. The lambda tensor that I defined is not part of the learning algorithm. That's part of the definition of the kernel, I would say. And Shou will discuss that later. So what I mean is, if you switch from gradient descent to SGD, or if you switch choice of loss, or if you switch learning rates, maybe the simplest one to talk about is switching learning rates. If you have a quadratic loss, then anything you do, right, is going to get you to the same place. But that's not true in this quadratic model.
Yeah, it's just in a sense. So the choice of parameterization is already, you can think of it as being an algorithmic choice, right? And that will change the picture here, even for the linearized model, right?
I think I would just say the same thing that I said before. The lambdas we're thinking of as part of the definition of the model, and then we're thinking of the learning rate because they don't go into the dynamics. The definition of the kernel doesn't go into the dynamics. So we're just talking about the dynamics here.
Okay, I don't understand this, but maybe we can talk about it after.
I mean, perhaps the simplest thing is just, does the ODE limit and the gradient descent discrete limit give you different answers, right? That's a very simple question. Does the choice of learning rate matter? For the infinite width network, it doesn't. For this, it does.
Okay, all right.
Kevin?
Yeah, thank you. I just had a quick question. I'm curious, have you tried to carry out this inverse algorithm engineering using these algorithm projectors in any sort of specific concrete toy example?
No. I mean, I think you can, you could look at the prediction equation. If you know something about your data, you could pick projectors. Have I tried to figure out a different algorithm that you get from that? No. I think it might be hard in the same way that having a kernel and trying to figure out the features is hard, but may be possible. And maybe there's just general intuition that we can get from doing it. I think it's exciting. We haven't had a chance to do it yet. You should
Okay.
you should do it and tell me about it.
Okay, great. Thank you.
Yufan?
So my question is, can you just compare the prediction performance by just looking at the this algorithm projector thing? I mean, like you just compare like two different algorithms by looking at the equation you have. Can
Yeah,
you do that?
Yeah, that's great. That's exactly the point. So I mean, so all this depends on the data set, right? These are all, so beta is from your test set, alpha is your the alpha indices are from your training set. So I expect that for different data sets, there will be different optimal algorithms. And I mean, that's in some sense what, when we say that Atom is good for NLP problems, but SGD is good for computer vision problems, right? There's some sort of data domain, and we're trying to figure out that there's some inductive bias for some algorithms being good in one domain and some good in a different domain. I mean, I'm told what I just said is empirically true. I don't know, theoretically if that's true as a fact. But the point here is that for a particular data set, this tells you, there's going to be what algorithm is good is going to depend on the data set. And so, I think that this is very exciting because you can analyze formulas like this and figure out for either for different domains, or even better, understanding the types of properties or the statistics of your data set that then lead to being able to pick different learning algorithms. So like in the best case, what I imagine is that we could take a data set, compute some simple statistics that are very quick, and based on those statistics, it will tell us how to pick our learning algorithm. For instance, it will tell us how to pick the hyperparameters of the learning algorithm a priori, and then we can save a lot of time training. So like this will help practitioners. That's the goal. Varun?
So hey, let me interrupt for a second. Do you guys mind taking this offline somehow? We're just about to start the next lecture. I don't want to be too late, just because people might tune in for one, but not for another.
Great.
And then there's the symposium and stuff after.
Fine.
So let's
yeah. Can I just say, please ask me
later.
questions in Slack, and we'll figure out a way to answer them. And thank you. And sorry for going over, Boris.
No, it's all good. I just want to make sure we don't end up pushing the symposium and stuff. People had constraints, that kind of thing.
Great.
Yeah, thanks again, Dan. That was really nice. Whenever you're ready, Misha, go ahead.
Yeah, sure. Let me just, I'm going to share the screen. Does this work? Can you see the screen?
Yeah, that's great. I think we can see everything. Okay, so we have Misha back for the second exciting lecture. So I'm personally very excited. So please take it away, Misha.
Thanks, Boris. Yeah, so we finished at this point in the discussion why bounds fail. And one thing I would like to do, I thought it would be useful to actually see a specific example which approximates a little bit more closely what happens in real, in sort of real practice, so to say. And this is an example specifically for MNIST, but you get something quite similar for other data set. And let me explain what's going on here. So all of this on this graph, the x-axis corresponds to the epochs, and this is eigenvalue, which is just it's a preconditioned stochastic gradient descent. You could just think about it as SGD, some fancy version of SGD. And what is being trained here is actually a kernel machine. So kernel machine in this case is being trained like neural networks. And there are actually some really interesting aspects of this, which maybe I'll discuss toward the end of the last lecture. But so the interesting thing here is that what you see is that so the top figure here is classification error. The middle one is the square loss and on the test, and the bottom one is the square loss on the train. And what you see is quite interesting. And so the different colors correspond to different kernels. You can just concentrate on the red color, which is Laplace kernel. So let's see what is happening here. So as you train your machine longer and longer, the training loss goes down, and it goes down to something like 10 to the minus 5. And the interesting thing here is that the test loss, both classification and the square loss, are going down monotonically. So bringing down the test loss, the training loss, does not seem to hurt the test loss at all. So that's a generalization. But of course, if you look at the value of this loss, this is 10 to the minus 5. And this is something much larger. It's like 6 times 10 to the minus 2. So it's a much, much larger value. So there is a big gap between test and train. Now, does early stopping help here? And you can see that for Laplace kernel, it actually doesn't. For classification for the Gaussian kernel, it seems to be helping just a little bit. So if you look at this point, it's just slightly better than the point all the way to the right. But the difference is very small, and this is quite consistent. So there may be some advantage to doing early stopping, but this advantage is certainly not big enough to sort of, it may be important in practice, but it doesn't seem that it's fundamentally that key. Certainly, if you can view this as overfitting, it's very, very minor. So that point is just maybe slightly, oops, sorry. This point is maybe just slightly worse than the middle. So this is kind of a summary of this. So SGD train error goes down roughly to 10 to the minus 5. SGD test error also goes down, and it sort of saturates. And what level does it saturate? It saturates at the interpolating test error, and this interpolating test error is obtained by not training this method iteratively, but just doing direct matrix inversion, as I discussed last time. And the trailing loss, the square loss of that interpolate is much, much smaller. It's 10 to the minus 20. So you see that from a practical point of view, from generalization point of view, there is really no difference between, running it for some time and stopping, and, doing it exactly up to numerical precision of a computer. However, and I should point this out, if you actually want to do this in practice, early stopping is a good idea, right? Because you can get something which is quite good, essentially the same as trading it all the way, with just 10 epochs. So there is practically really no reason to drive the error so low. But the important aspect of it is that it doesn't hurt. So this is kind of arguably the best practice for deep learning. And I really like that quote from Ruslan's tutorial 4 years ago. He said the best way to solve the problem is you build a big system and you want to make sure you hit 0 trading error. I think it's probably he meant here for classification rather than for regression, but the idea is very similar. Now, he didn't suggest that this was the kind of final stage. After that, you still do different stuff, you tune the model. But if you just stop at this point, as we have seen before, you already get a good result. So perhaps you can say that the reason this observation, of course, as I pointed out, is much older, going back to Bryman and going back to work on the margins in the 90s. But the point is, I think what's different now is that it's actually quite close to what people do in machine learning, in deep learning. Okay, so this is perhaps the puzzle, is it sometimes referred to generalization, is that interpolation does not appear to overfit, contrary to widely held beliefs in statistics and machine learning. And yet, the practice of deep learning is arguably closer to interpolation than to classical settings. And I would like to make a couple of sort of more maybe philosophical points here, is that in some sense, we're kind of taking a very physics-like approach to the problem. Is that in what sense? Is that we're observing some phenomena, in this case, that interpolation doesn't seem to overfit. And we're trying to come up with a mathematical explanation of what we observe. So it is a lot like physics, except that our phenomena happen in a computer, or in some sort of combination of computer and real world. We're dealing with real data often. So that's one thing. And I was thinking about this kind of analogy of Jan LeCun of looking under the lamppost, and which is, I think, a fair criticism of some theory. But I think we have to be careful because, well, why is looking under the lamppost for lost keys? Why is it a bad idea? Well, if you think about it, the lamppost is actually a very useful thing, right? But it was not built for the purpose of finding lost keys. It was built because we want, people to see where they're going in the street, and maybe it's safer and nicer to, walk when there is light. If you want something which will help us to find the keys, right, we would like a flashlight. So looking at the lamppost is actually a lazy way to use theory. What we need a flashlight. Well, we don't know what kind of flashlight or what kind of tool exactly we need, but it does seem that interpolation actually provides us a flashlight which, eliminates one aspect of what is happening, of the real phenomena, and it gives us some sort of theoretical way to approach these things, and we'll discuss this in a minute. Okay, so clearly, new theory of induction, to use Vapnik's term, cannot be based on uniform laws of large numbers with capacity control. So can we somehow provide some other theoretical framework for interpolation to generalize? And that is sort of probably the first question. And the answer is, well, there is one method, one classical method, only one, as far as I know in any case, which interpolates and for which we have theoretical guarantees. And there is a caveat to that, which I'll mention later. But essentially, there is only one, it's very well known, and it is one nearest neighbor classifier. And one nearest neighbor classifier has a very nice performance guarantees going back to Cover and Hart in the 60s, which says that the loss, the classification loss for one nearest neighbor classifier is twice the base risk. And let me explain very briefly how the analysis goes, just sort of informally. And I'm going to switch to iPad. It's easier to draw there. So I hope everybody can see. So imagine I have here, imagine I have a very simple setup, and you will see where twice the base risk comes from. Oops. So I have my space, and I have some points here, and let's just assume the uniformly sample square, and so xi are uniform, and probability of one given xi is simply equal to p, and you can just think about it as 0.1. Okay. So 10% you get one, and probability of 0 given xi is equal to correspondingly to 1. Okay. So you are more likely to get 0 than 1. So in that case, the optimal predictor, the base optimal, is just simply f star of x is 0, right? Because for classification, you would always classify every point as 0. It's just like a flipped coin. So let's see what one nearest neighbor do. And one nearest neighbor does something pretty cool. So if you think about this, and maybe I should make a bigger picture. Imagine I would have 3 points. And suppose I have a new point here. Then I'm simply looking for the one nearest neighbor of this point, right? And I will assign the label of that point to my test point. And how does it do it? Well, if you think about what it does, it actually, one nearest neighbor essentially does what's called Voronoi tessellation. So you split the plane into these polygonal regions, each one of which is closer to one of the specific points. So Voronoi tessellation. Now let's think about it. What is actually going to happen? So ideally, of course, because I know my probability distribution, I would just predict 0. But one nearest neighbor is not quite going to do that, right? One nearest neighbor is going to take the closest point, and the closest point with probability p is going to be 0, but with probability 1 minus p, it is going to be sorry, the other way around. With probability, maybe I should call this p rather than the other one. And this is equal to 1 minus p. So with probability p is 0, and with probability 1 minus p, it's going to be 1. So with probability p, I will make the right choice, and I will assign this to 0. If with probability 1 minus p, I'm going to make a mistake and predict the wrong thing. So I'm going to predict the wrong thing. So F1 nearest neighbor predict 0 with probability p and 1 with probability 1 minus p, right? So now you can see that when I predict p, my loss is going to be 1 minus p, if you will. I'll leave it as an exercise. And when I predict 1, my loss is going to be p. So actually what I'm going to have is that the base risk, the expected loss is equal to 2p times 1 minus p. And in this case, it's going to be, well, actually it's equal exactly to 0.18, right? So the best predictor will give me a risk of 0.1, but this predictor gives me roughly twice, because you see there is this 2 here. So it's roughly twice. So the twice is about. Okay, so that is what's happening here. And you can see the problem is that there is some of these regions, the regions which correspond to the noisy points, are somehow misclassified. And the probability of hitting one of the region is exactly p. Okay, so now can I fix it somehow? Can I make an interpolation? So this is great, but this is not completely satisfactory because, well, I have this loss, which is a lot worse than the best I can get. Can I get much closer to the optimal? That's a really interesting question. And the answer is, and I have unfortunately to share back to this. And the answer is yes, and I can do a lot better. And the procedure is actually quite simple. It's something that you may call simplicial interpolation. And how does simplicial interpolation work? It's basically the following. So what I'm going to do, suppose I have this 5 points. I'm going to triangulate this point. So I'm going to build these triangles. And suppose now this label at the blue point is 1, and these are zeros. And you can kind of think of this point being the noisy point, right? Well, maybe my real prediction should be 0, but once in a while, because of the noise, I'm predicting, I'm getting this noisy data. You have images of cats and dogs. Once in a while, a cat gets, for whatever reason, identified as a dog in your training. So what I'm going to do, I'm going to triangulate, and then I'm going to linearly interpolate between these 3 points on each of the simplets. And how do you linearly interpolate? Well, here is the key observation. When you have 3 points in 2 dimensions, there is a unique linear function which takes specified values at the vertices of the simplex. Of course, this function is different on every simplex, but you can see that they must, because they're linear, they must actually match on every edge. And this extends to high dimension. Instead of triangles, you will get arbitrary dimensional simplexes. So I linearly interpolate, and then I'm going to threshold this at 0.5. So maybe actually in practice, it's easier to think instead of 0 having -1. So you have 1s and -1, and you just threshold this at 0. And an interesting thing happens when you do this. Is that, let us think now about the area which gets misclassified. And let's compare one nearest neighbor to the simplicial interpolation, just in 2 dimensions. So if you do one nearest neighbor, you see that the area which is closest to this point is exactly 1/3 of the triangle. Because, well, it's easy to think about this, because if you just drop a point at random uniformly in this triangle, every one of the vertices is equally likely to be the closest point. So this area must be exactly 1/3, just from basic symmetry configuration. I'm actually, okay, I'm assuming that this triangle is equilateral, but I'll say something about why this is not important. Let's look about simplicial interpolation. Well, simplicial interpolation, you have 1 here, you have 0 and 0 there, and it's a linear function. So if you look where this function is equal to 1/2, where it's closer to 1 than to 0, you will see that actually it's also a triangle, and this triangle is similar to the original triangle, and it has exactly 1/2 of the base. So, well, the area goes proportionally to the size of the triangle squared, and therefore it's 1/4. So one nearest neighbor, the bad area is 1/3, but for simplicial interpolation, the bad area is 1/4. And the key observation here, this difference depends on the dimension. And let me explain this in a little bit more precision. I'll switch back to the plan again. So we have, so imagine I have this kind of pyramid. And I have the value 1 here and have value 0 there. And then if I would like to look at the area of this pyramid, where the linearly interpolating function is bigger than 0.5, it's actually going to be the top of the pyramid, whose area would be 1/2 cubed compared to the area of the whole pyramid. So we see this dependence on the dimension coming in. So in high dimension, there is less and less area around the bad point. And this is kind of the bad point. So that's the idea. Now let me point out a couple of geometric aspects of it, which are kind of nice. First, there's not that I said, okay, equilateral triangle, but it actually doesn't matter. The shape of the triangle here, the shape of the pyramid doesn't matter because, well, any two simplices are equivalent up to a linear transformation, right? Because think about two triangles, right? If I have one triangle and I have another triangle, there is some linear transformation which take this vector to the corresponding vector of the other one and that to that one. That transformation, of course, changes areas, but it doesn't change the ratio of the areas. So this is neat because actually this exact argument works for any triangle or any pyramid. So shape is not important. So that means I could take any triangulation. So any triangulation works. The only thing which I didn't get mentioned is that you cannot have very big triangles. Why? Because you see, I'm assuming that probability of a specific point being noisy is the same for every vertex of the triangle. This is close to being true if your probability function is continuous, if your conditional probability is continuous, and the triangle is small. But if the triangle is big, of course, this can change. So you need sufficiently large triangulation for this to work. You need, I shouldn't say sufficiently large, you need enough triangles so each triangle is kind of small. So this works when there is a lot of data. Okay. So now, okay, I've said that one point, of course, here is this noisy point. But in general, of course, I can have some fixed number of points, which are some proportion of points, which are noisy point, right? So I would like to have a proportion of points are noisy. And let's say this proportion, so probability of one given x is, let's say, p, as before. So if I have d points, so for d points, roughly p times d, so d vertices, I should say, vertex points, roughly p times d of them will be quote unquote bad. And now what you can do, actually, you can do the computation, and this follows from the sort of standard concentration. And here is the idea. The idea is that so first notice that you can do it for a standard simplex. And a standard simplex is simply if this is E1 and this is E2, then the standard simplex is this one, and I can put E3 here. And this is training my artistic abilities. So it's simply the set of points that sum alpha I EI such that alpha I is greater than 0 for all I, and sum alpha I equals 1. So this is the standard simplex. And now I want a uniform probability distribution of a standard simplex. Why is it uniform? Because I'm assuming that for a simplex which is sufficiently small, the probability distribution doesn't change too much. So that's the assumption. You can, of course, you can incorporate changes, but then you have to explicitly think about the size of this triangle. So now how does it work? Well, we know that roughly, okay, this is actually called the Dirichlet distribution. You can explicitly compute from this, but there is an easy way to think about it. Just think that you're choosing each alpha I from interval between 0 and 1, right? Uniformly. That is not going to give you a simplex because you will not have the sum being equal to 1. So you just divide them by the sum. So that's equivalent way to think about it. And then if you think about what happens, you can say that expected value of each of this vertex to have y equals y is exactly p. So the expected value of the sum is going to be p times the number of them. And then you have to deal with the numerator, which is actually not hard because the numerator will concentrate nicely. So you would basically see is that you will get on average the expected value. So expected value of your predictor. So expected value of simplicial interpolation is going to be something like P times D, and you will pay a price which is because of the uncertainty, you will plus or minus something like square root of D. So if you work it out, so square root of D is a concentration. It's a standard deviation of the thing. Well, when D is large, right, P times D should be much larger than square root of D. So what you would get is that P is smaller than 0.5. This value is likely to be smaller than 0.5 on almost all points in the simplance. It's the same thing as what I said before, but done through this concentration. I'm not going through the argument because there are all the technical details which are not crucial to understanding this. And there is a question, Christian?
Hi, yeah. This may be trivial, but how do you generalize this simplicial interpolation to multiple labels? It seems like there might be a problem with ordering. For example, if I have like plus minus 1 and 0, then if I just take linear interpolation, I'll have like the label 0 in between 1 and minus 1. If these are
so you can encode multiple labels as vectors and you can interpolate in this multidimensional space. It's not really so much as a practical algorithm, it's more of a demonstration. Then you can do a lot better than one nearest neighbor, and that somehow the dimension comes in. So you shouldn't think of something, it can be implemented, of course, but it's not so important. It's the more interesting thing is that actually, let me just point this out. It's, let me switch back. Sorry, I'm switching back and forth too much.
Misha, maybe before you switch too far, did you mean to divide by D in your last formula? Like,
yeah, so thank you. The last formula.
Right,
yeah.
because otherwise, I don't know why you're.
Yeah, of course. It has to be divided by D, and if you do the concentration for the denominator, you will see it will concentrate around D because it's a sum of
exactly.
uniform distributions, right? Of D uniform distributions. So basically the numerator is P times D plus minus square root of D, and the denominator is D plus minus the square root of D. If you divide this out and do the computation, you will see that the expected value is exactly P. And in fact, if you do the concentration correctly, you see that it concentrates quite tightly around it. So that's basically what you can get. And so the theorem is you get something like this. If depending on how exactly you pose it, you either get exponential in dimension or you get polynomial dimension. I put here the kind of nice one. I'm assuming that these probabilities are strictly separated, that you can get 1/2 to the D. So in any case, the point is that this bound gets closer and closer to the base risk as the dimension increases, and sometimes exponential. And this is much better than the classical one nearest neighbor, because for nearest neighbor, you just have this factor of 2, right? Here you have 1 plus 1/2 to the D. Interestingly, you get this blessing of dimensionality. Somehow in high dimension, there is more possibilities for you to feed data and yet not mess things up too much. Okay, yeah, any questions? Yeah,
yeah, quick question. This interpolation sometimes reminds me to the hat function in PDE, in numerical PDE. Can you use, instead of linear interpolation, a quadratic polynomial or a third order polynomial and you have something similar to a kernel method?
I believe it will also work. So informally, I say yes. So practically, certainly you can. From a theoretical point of view, the nice thing here is that linear is quite easy to analyze because you have this Dirichlet distribution of the simplex and it's invariant to the shape of the simplex, right? Because this is the key point, is that you can analyze a standard simplex because the ratio of these areas is invariant. I'm not sure that would be true. I think actually it will not be true for more complicated interpolation scheme. So any analysis would be much more involved, but I don't see why they wouldn't work the same way. You just need to have the same kind of feature that they localize by points.
Thank you.
There was some other question. No? Okay, I'll continue. So that's basically a kind of basic idea that yes, you can do much better with interpolation than one nearest neighbor. You can get pretty close to being consistent. Of course, being consistent is basically saying you would have the actual base risk when you have enough data, right? That's what consistency is that as you have more and more data, you approach the optimal. This is not quite approaching the optimal, but it gets closer to the optimal. And it turns out that you can actually get like real consistency. And let me very briefly describe the scheme that you get with that. And I first would like to point out something which is kind of interesting. It doesn't relate to interpolation directly, but so let's look at this scheme. So suppose I have y's, and again, I have y's which are, let's say, ones and minus ones, so ones and zeros. And I am going to write a predictor in the following form. F of x is equal to sum yi k of x ix divided by sum of k of x ix. Yeah, Karthik, there is a question.
Professor, sorry to go back, but the previous bound, you said it doesn't give a consistent estimator, but as d goes to infinity, doesn't that exactly approach base risk?
Yes, so it gives you consistent estimator in the infinite dimensional case.
Right.
But it doesn't give you a consistent estimator in a sort of traditional statistical sense as data goes to infinity and d.
Oh, right, it's d going to infinity, not
d, not n.
Perfect.
So I think about it as near consistency, right? When d is high, you're like, imagine your d is 100, right? And you're maybe within 1 over 2 to the 100 away from consistency. So in practice, who cares? But it's still nice to have to have result that you can get exact consistency. Okay, so what do we have here? This is not the right. Okay, one more question and then I'll continue. Siddharth, please.
Yeah, hi. I understand this idea of simplicial interpolation and seems like a good idea, but what I don't understand is there is still a need to have a metric which organizes the points neatly in the simplex, right? And how do you get them this metric from a neural network, say?
Oh, you're asking how it relates to neural network, right?
Yes, but
I'm not saying it relates to neural network at all. It's just a different method, right?
No, I mean, it also assumes like the points are like neatly arranged on the simplex, right? At the first place itself. Or you can have this assumption that you is like before you even consider this interpolation, right?
What do you mean neatly arranged? You can triangulate. Oops. Let me just. You can triangulate any points, right? If I have some points here, they don't have to be neatly arranged at all, right? You just triangulate them. That always exists.
I mean, if there's a large density of, let's say, wrongly labeled points in between here and the other points, then.
So when you triangulate them, you don't care how they're labeled. You just triangulate the axis, right? You only care about the labels to construct a predictor. So you get your axis. You don't care how they're labeled at all. You triangulate them. And I'm sort of not worrying right now how exactly you triangulate them, because it can be complicated to build a triangulation, but it always exists. That's all you need to know. And then on each one, you build this kind of function. So you get this piecewise linear function on the whole space. And the claim is, as long as there are more good points and bad points, your prediction will be close to consistent.
I see. Thanks.
Okay, great.
One more question, Shed, or like, I think it's very brief. I mean, you say it's the blessing of dimensionality, but it seems like when D is large, you also kind of need like 2 to the D points to even see your space. So
yes, absolutely, Boris. It's well, okay. I shouldn't say the blessing of dimensionality. It's a blessing of dimensionality. But there are also courses of dimensionality, right? So you have the thing somehow playing off in some complicated way. So in this case, dimensionality helps because it makes it more consistent and somehow makes it easier. But in other ways, it hurts because you have to see more data somehow.
Right. Okay.
Also,
thanks for
constructing these things is more complicated. Yeah, thanks. That's a good point. Okay. In any case, so let me go back to this Nadaryev, or go forward to this Nadaryev-Watson schemes. And the idea is actually, it's a really neat algorithm, right? So you have xi, yi pairs, and you simply construct this function of the following form. And k here is, for example, Gaussian kernel. So traditionally, it's Gaussian kernel is very. Why am I having issues with this thing? So something like that. So now notice that there is not an interpolating scheme at all, right? Because if you actually read off the value at one of your training data points, it's not going to be equal to yi. It's some sort of smoothing schemes, right? And the way to think about it, you have this Gaussian kernel, and you're kind of averaging things around your point with the weight being given by this Gaussian kernel. So that's really the way to think about it. It's smoothing, or maybe you can think that this is nearest neighbor scheme with a weight. It's a kind of equivalent way to think about it. And there is a lot of classical analysis of the scheme, and they basically show that if you choose these parameters correctly, that you get nice, consistent for regression, for classification, various rates, and so on. The massive literature. One thing I would like to point out that if you don't care about regression, just care about classification, you don't need the denominator, because things that yi's are positive and negative, you just care whether the denominator, whether the numerator is positive or negative. That's all. So it's kind of nice because if you want to classify, you can actually get rid of the denominator. Makes analysis much simpler. Now, if you think about this, so let me point something out here, is that if you get rid of the denominator, the function form is actually of this form. It's sum alpha I k of x I x. Okay, this is my predictor. It's equal to this. And what is this thing? This is exactly the same form as what we discussed before when I said Laplace kernel machine and so on, Gaussian kernel machine. Actually, the functional form is exactly the same. For classification, for regression, it's slightly different, but still very similar. But notice here something quite interesting. It is that this is a direct method in the following sense. There is really no optimization, no matrix inversion, nothing, right? You just write down the sum and then you read it off at new points. It's actually a really neat way to do it. But there is no optimization involved. What I discussed before is something quite similar to this in the form, but very different way of choosing coefficients. Because remember, I said that the coefficient of this is NW scheme. And this is a kernel machine. And for kernel machine, alpha is equal to k minus 1 y, where k is this matrix, that kij is equal to kxi xj. Okay. So same functional form, very different way to choose coefficients. And this is some sort of inverse method. Why? Well, you have to essentially solve an equation. You have to invert this matrix. Now, if you think about what neural networks and essentially all methods which are commonly used are doing, except for nearest neighbors type of methods, they're actually inverse methods. And it seems that inverse methods in general perform better than direct methods, although I don't think we have any theory for that. It's actually very puzzling to me. I don't think there is any sort of theorem saying that inverse methods have to work better, but they seem to do. They seem to be. Of course, whenever you have inverse method, you can optimize it by some sort of iterative procedure. Like instead of computing the kernel, inverse kernel directly, right? You can do some SGD or gradient descent type of optimization. Okay, so how do I now? Yeah, questions?
Professor, just regarding the last point about inverse methods versus traditional mechanism, mathematically they should be equivalent, right? If there is a difference, it should be in the optimization.
What do you mean mathematically? The equivalent? I mean, they're obviously not equivalent, right? Because for, oh, I should say alpha I here is equal to yi, right? Oops, sorry.
Oh.
I mean, it's obviously mathematically not equivalent, right? Because in the first one, alpha I is simply yi. In the second one, alpha is inverse of the kernel matrix times y.
Oh, got it.
Very different ways.
Right, I misunderstood. Thanks.
Yeah. Any other questions? No. Okay. So yeah, I think there is something fundamental going on here, but
well, they are equivalent if k is the identity.
Yes. Actually, they're equivalent in some really interesting case, which I'll point out in a minute. But they seem to be not equivalent in sort of practical. Practically, it seems that kernel machines just are better, but theoretically, I don't know. Yeah. So when k is identity, or when k, let me get to this point in a second. The equivalent is interesting. So how do you make that scheme interpolating? Or what? I mean, this is obviously not interpolating scheme, and classically people have not thought about interpolation at all. But actually, there is a really simple way to make the scheme interpolating. And in fact, it was known in a different context, and it's known as Shepard interpolation in geospatial data. And this guy, Shepard, actually was an undergraduate when he wrote his paper back in the 60s. And the point there is that you can take this kernel to be an unbounded kernel. And what do I mean? I mean a singular function of this form. And just assume alpha is 1. It's really not for this discussion. So think about k being 1 over distance. And you can say, well, how can I do it? But think about what is happening here. This, of course, is a singular function, the denominator, but actually the singularities of the denominator and the singularities of the numerator are the same. And it's not easy to check. It's not hard to check. It is easy to check that actually they cancel out, and this whole function is continuous. So you get this function, which is continuous, and it fits data exactly. How do you see that it fits the data? Well, because think about what happens when x is equal to xi. The numerator is infinite and the denominator is infinite, and it's exactly the same up to the coefficient 1, because all the finite terms are kind of getting killed by the infinity, right? I hope this is clear, right? Because think about, it's a sum, but one of this term is infinite at the sum, so you can kind of ignore all finite sums, and the same happens in the denominator. So they cancel each other out except for yi. So f of xi is equal to yi. That's the option. As before, if you only care about classification, you don't even have to worry about the denominator, and you can just look at the sign. You don't even care. So this is kind of neat. You can take different functions here, but basically you just need a singularity. And there was a remarkable paper by Devroy, Georfi, and Kruzak, I'm probably mispronouncing it, in '98. And they consider the scheme, a specific type of the scheme. They call it a Hilbert scheme because of the Hilbert transform, which uses something like this. And they proved that it was actually consistent for regression, remarkably enough. Turns out that it's not just consistent for regression, it's kind of optimal by choosing these parameters correctly. And I don't want to go too deeply into this, but basically, if you use this as a nearest neighbor scheme, so you do the same thing, but you do it over nearest neighbors, and you choose a parameter correctly, it's actually an optimal scheme in some sort of statistical sense. And it works in any dimension, and it works for classification, and gets fast rates and all this nice stuff. So somehow by using this Nadaraya-Watson type of predictors, you actually can get pretty practical methods, although they may not be the best, but it's easy to implement, and methods which can be shown to be statistically consistent and even optimal. And to demonstrate how it works, just on a specific example, here is one example. And the data here are y equals x, so it's a regression problem, plus noise. So y equals x plus some sort of random noise from a normal distribution. And this little points are data. So the optimal predictor would be the line, because that's how the data generated. This scheme, interpolated nearest neighbors, this is with log weight, gives you this red curve. And you can see first that this curve is continuous, but it's very, very spiky. It has discontinuous derivative, which you can actually figure out by looking at the previous one. So it's a simple exercise to prove that it's continuous, but has discontinuous derivative. The neat thing about this is that you can see where this sort of consistency comes from. Is that at every data point, you're quite far from the blue line, right? So at no data point is your prediction correct prediction, quote unquote correct, what the optimal predictor would do. Someone who already knew your model would just predict the blue line. So really you should predict this point, instead you're predicting that one. So it looks like it's doing really bad. But if you look at an average point, you're actually not very far. So you take some point at average and you see that it's pretty close to the blue line. So on average, your prediction is actually quite good, even though like you're completely messing up on your data. And that's because somehow the scheme allows you to feed the data in the spiky way. So you're not overcommitting to every noisy data point. You're averaging enough away from specifically your data points. And I see that there are some questions. Please go ahead. I don't see who is asking it.
Yeah, sorry. Is there a bound we can use on the expectation of this classifier here? Because I mean, it's so spiky, it's so discontinuous and so complex. I mean, how good can it actually predict on a test set?
Optimally, right? It's statistically optimal. No, okay. There are the standard statistical ways to measure optimalities, right? Minimax, right? You can say, okay, do this. It's like, how good are those measures? And the answer is, well, it's up to you what to make of them. But this is certainly the way that, in statistics, people have been measured optimality, one of the ways. So in that sense, it completely passes that. Despite being, as you pointed out, very, very spiky. And apparently complex. So somehow apparent complexity here is hiding some sort of simplicity. And you can see also why uniform bound would really struggle with something like that, because how can you, this space of functions of this form is like ridiculously complex. So how can you have some uniform bound? Like uniform bound, you have something has to be true for every function in this class. But that would be ridiculous to expect here. It's not that every function of this form is good. It's just the function that you choose based on your data is good. Okay, more questions.
I sort of actually have a question about this, Misha. So I think you're kind of saying with these pictures that, there's some secret epsilon, which if you're epsilon away from a training point, you're basically just doing the weighted nearest neighbor thing, however you want to interpret it. And, and that's pretty good when you're truly trying to extrapolate. But, but precisely by adding a very localized spike, when you're closer than epsilon, that's what allows you to be like completely consistent in the end. Like you actually also locally fit the data without messing up the global. Like, you trade kind of global oscillations for local peaks or something like that.
Yeah, I think that's a fair way to put it. And the question is, you may say, okay, well, am I not cheating by doing this? And you can argue that this is some sort of cheating because, yeah, I'm fitting the data really well at every data point, but away from them, I'm somehow averaging, even though it's like not completely obvious that this is what it's doing. But it's true, right? There is some sort of implicit averaging here. And the question is, why should I care? And the reason to care here is, I think, the following, is that maybe you don't care about, well, actually, okay. So there are a couple of reasons. Okay, well, first, actually, people do use this specific scheme or something very similar to this. This is Shepard's interpolation. So this is a really, usable scheme in practice. Because more fundamentally, this, I think, nails something down, or I hope nails it down, this connection that deep neural networks are doing something similar to this, but in a way which is even much more less transparent than this. So that's I think that I think is the kind of maybe a more important conceptual point here.
I see. So you're kind of saying that in a deep neural network, let's say you take something that's very wide, somehow the depth encourages the kernel to itself be more spiky. And when you do the kernel regression, you're looking closer to this. That's kind of the point you're making.
Yes, and what we see is actually high dimension helps with this because it gives you somehow more degree of freedom than you can put the spikes without messing the global picture up. So that's where the blessing of dimensionality comes in. It works even in one dimension, but actually, if you write down the condition that you need on this kernel, you realize that it's less restrictive in high dimensions.
I see.
So yeah, so I'm thinking of this not necessarily as that this method, like you have to really care about this particular method, but this is a flashlight. Like we don't want to look at the lamppost, right? We want a flashlight, and this is one perhaps flashlight which allows us to shed some light on what's actually going on in deep learning. And I'll get more specifically to the things which are more like deep learning. So that's yeah. Any other questions?
Can I ask a question? So, assuming this picture is true, we can see that if we interpolate, like if we linearly interpolate between 2 points, so have convex combination of 2 points and test on them, this curve would perform differently as compared to, let's say, just the straight line predictor. And we could perhaps do a similar test for in the case of neural networks and maybe check out some inkling of this hypothesis or not?
I'll discuss specifically the evidence we have for neural networks, and I think some of the work that Andre is presenting is closely related to that as well. But yeah, actually, if you think about what happens with linear interpolation, say I do simplicial interpolation here, right? I would do something like this. Okay, I cannot draw it, but it would be this very jagged linear curve, which is actually not going to be that good. And there is a good reason, because it's only dimension 1. So this blessing of dimensionality doesn't really help you here. But with this log weights, it even works in dimension 1. So in some sense, this also shows, I think this sheds light on something quite fundamental. You know, for a long time, we've been really worried that fitting noisy data is a bad idea. Everybody's had that essentially. And this actually proved that this is not true. There is really no reason, no a priori reason to think that this is a bad idea. Because would you do better if you didn't fit this data? It's not clear. Maybe in this particular case, if you knew already that it was linear, okay, you can do linear regression and you would do better. But suppose you don't know that it's linear, right? Well, how would you figure this out? Okay, yeah, and K is the number of nearest neighbors. Okay.
Can I ask a question? So I had a question regarding your comment that you said inverse methods are usually better in practice. However, this is kind of like a weighting scheme, I guess. But you said it's optimal. Min-max optimal. Yeah.
How does that in practice relate to optimal, right?
Yeah, like how does inverse methods compare to this?
I don't know. First, we cannot even necessarily prove that inverse method would be minimax optimal. I mean, there are some specific proofs now, but it's not so clear in general. Yet they seem to be better in practice. So there is clearly something which minimax optimality is not captured. But this is not a bad thing in practice. This will work. This actually works. It's just that it doesn't quite work as well. And I'm not sure why. But let me discuss one more somehow implications of this, and then I'll be happy to take more questions than writing out of that. But here is a curious corollary of this. Well, so suppose we take this seriously, right? And as I hope we do, then think about it. Around each one of this, so think about classification, right? For classification, you just have 0 and 1s. Then around each one of the data points, which is somehow noisy, right? Which should be you should predict a cat, but it's a dog for whatever reason. And we know that some fixed percentage of them are like that. So let's think about what happens. Around each one of them, there is now a little basin, a little set, where everything will get misclassified. So instead, because just by some accident, this happened to be a cat instead of a dog, everything sufficiently close to it, because you have this interpolating schema that's continuous, everything sufficiently close to that will actually be misclassified as well. And now think about it. Say 1% of my data is misclassified, which is what happens in practice, right? Some fixed percentage of the data usually misclassified. So that means that as I get more and more data, I have this small, but everywhere dense set of bad prediction. So what I'm going to have these basins of misclassification, they're everywhere. They're like rational numbers. But I do have very small measure because I know that in the limit I'm consistent. So the measure goes to 0, but the coverage goes to 1. So exactly like rational numbers. So this is pretty interesting because this actually suggests that this interpolating classifiers has some pretty weird behaviors. They have this misclassified example. So around any point, you can go a little bit and find an example which is misclassified. So around any cat, there is a dog which looks very similar and is misclassified as a dog. And remarkably, this actually is what happens in deep neural networks. And it's exactly phenomenon of adversarial examples. And basically, the idea is that if you take a dog, and this was originally, I think, in this paper, Intriguing Properties of Neural Network by Szegedi and co-authors, you take a dog, you add just a little bit of noise, which is actually visually not perceptible, and suddenly neural network classifies it as an ostrich. So you can say that, okay, if you take the interpolated point of view seriously, this is exactly what you would expect. Your adversarial example have to be asymptotically dense, even though your predictor may be consistent or even optimal. And well, this has been actually a lot. There have been a lot of really work on this adversarial examples recently in the last 3-4 years. And I should make a sort of caveat here, in that I'm not claiming this is exactly the only mechanism by which these adversarial examples arise. But what is encouraging, and that's, I think, this indication, one of the indications that this is the right point of view, is that if you take the point of view of interpolation, you would immediately come to this conclusion. So it's very consistent with what's observed. This is a good maybe point to stop, and I'm happy to take questions, discuss anything.
I had a quick question about this particular slide. So the dog and ostrich, which one is raisin and which one is cookie in this example or in this analogy?
So you see this one is the little raisin, right? Because this is classified as ostrich, and so around. So think about this. Around every point, so there are many more of these raisins, and they're very tiny. So around any like good point, there is one of these raisins. They're dense in the bread. The raisins are dense within the bread. So this is a good point, and this is a raisin.
Okay. Thank you.
So is the picture you showed with the spiky red function, is that kind of a good mental picture to have when we think of interpolating neural networks, or is that too simplistic? I mean, well, we know they have zero or almost zero training loss, but is this kind of picture of a spiky function, is that a good mental picture?
Well, so it depends. I think they're actually probably more like this, because they deal with high dimension. So the spikes are not so extreme, right? When you think about simplicial interpolation, you don't think it's just a linear function. You don't think of spike being so extreme as this very sharp one. So I think they're kind of more like this picture rather than the other one. But I think as an idealization, it's a good thing to keep in mind. So the way I kind of think about it, it depends what you're trying to achieve. If you want something a little more realistic, this is probably a better picture. But if you want to identify the phenomenon, that may be the more sort of extreme view. Like in physics, right? We model planets as points. Planets, of course, are not points at all. But if you just look at the orbits and you write, the law of gravity and so on, thinking of it as points is okay. To the first order, it's pretty good. So it depends what you want to try. What you want to try to understand, right? If you want to study climate, right, you kind of think of a planet as a point. If you want to study orbital motion, not a bad approximation. Depends on the level of detail. Okay, yeah, next.
Can you go back to the picture for the cookie and the raisins?
Yeah.
So over here, this is like a picture for only one interpolating predictor, right? So given an interpolating predictor, I'll have some type of raisin bread topology on my my sample space. Meaning if I have two different interpolating predictors, then or maybe many, then I could like, if I take some type of majority vote and stuff, I'm wondering if like the noisy data that like, if you were to add a little bit of perturbation noise, like in the next slide, if where the raisins are for different interpolants, they're going to be different, so that in average they should be canceled out in some way. I was wondering if that's like something that you've like read or like know anything about.
Yeah, so raisins cannot be canceled out because raisins relate to the data. So you have an optimal predictor. The optimal predictor says that this should be a cat, but for whatever reason, it's in your training data is misclassified in your dog, and no interpolating predictor will fix this. You could do something else. You can do some averaging. That's no longer interpolating, but you can get rid of it. So it's not optimal predictor doesn't have this raisin, right? If a priori optimal predictor does not have this. But imagine that my predictor is kind of like the optimal predictor, except it differs on rational numbers.
Oh.
Well, who cares, right? Because if you take a real number, right, it's not going to be rational. The probability of that is 0. So maybe you're not paying very much.
Gotcha.
But every interpolating predictor will have exactly the same raisins.
Gotcha. Okay. So there's no like ensemble thing that you can use that's gonna make the problem go away. So.
You can make the regions smaller around each region by
Gotcha.
but
Sense.
not get rid of them. Mm-hmm. I saw there were some other questions. Unfortunately, I don't see exactly somehow it doesn't show me who is asking. So I cannot. You have to somehow self-organize.
There's no one else. So on the same slide, in the case where like we believe this theory, wouldn't that suggest that a smoothed model, which like given a prediction, let's say an adversary puts us inside of a raisin, then the smoothed model can just perturb the input so that we go out of this measure 0 like space of raisins. We would expect that this would give us like a very good prediction, but I do not think that this is what happens in practice. Can you comment on this? Like maybe tension, or at least?
Yeah, so that's really interesting because in practice, yeah, you would think it wouldn't be very hard to get rid of this raisins by averaging of some form. Turns out really difficult in practice. I don't have a good explanation why. I suspect it's actually because there are other mechanisms which causes raisins in addition to this. And this mechanism somehow are not so amenable to smoothing. So it seems that in practice, the amount of smoothing you have to do to get rid of these raisins is quite large and really hurts your generalization. So you get some trade-off. In principle, there is no reason there should be a trade-off. You may be able to just smooth and get the same kind of result. But yeah, I don't have a good explanation. I mean, there is some really interesting work on this as well, like for example, Alexander Madrid at MIT did some trying work to understand the mechanism by which this adversarial examples arise. Hmm?
Okay, I'm not sure if there are more questions or not, but
I have one question. Sorry.
Let's do one more.
So can you go back to the plot that showed where the interpolation plot where the optimal predictor was a line, and then this one. So so the picture is that like the 10,000 foot picture is that when you have interpolating models that perform well, what's essentially happening is that it's pretty much close to the optimal predictor except for the spikes. So you show that this does happen for the nearest neighbor like models. Does the picture change at all when you have when you replace essentially the labels with the inverse kernel multiplied labels, basically the inverse models, or does it remain pretty much the same?
Yeah, if you do inverse kernel, it's not quite as spiky. Well, it depends which kernel you use. Oh, actually, here is a cool observation. And it goes back to the Boris's point. So imagine that I'm doing inverse kernel model. And I had this somewhere here. Yeah, here. So imagine I'm doing this inverse kernel model with a kernel which is singular, okay? So my kernel is actually singular. That means, what does it mean that the kernel is singular? That means that on the diagonal of the kernel matrix, if my kernel is something like 1 over xi minus xj, I have infinity on the diagonal of the matrix. That means that if I'm doing inverse kernel model, it actually works as an identity matrix because it's infinity on the diagonal, so I can ignore all other entries. You need to get the right scaling, but that's not really a problem because we're dividing it out. So this is exactly the point where it becomes identity. And in that case, for the singular kernels, direct and inverse methods are the same. So that's kind of interesting because there is this one case where you actually have the same answers.
Wait, so the kernel has identity on the diagonals, but when you invert it, wouldn't they be the inverse, like the opposite of that? Because the diagonal entries that were really, really large would become really small.
No, it will become small, but think about what happens when I have infinity on the diagonal and finite elements everywhere else. I could just ignore all the finite elements because infinity is going to dominate the whole thing.
Okay.
Imagine I am inverting something which is infinite, or I'm inverting something which is infinite plus finite. The result is the same because it's infinity which dominates. You can write it down as a limit, but that's what is happening. So essentially, you have identity matrix, and that's actually going to give you exactly the same form as the derived ones. So it's an exercise to sort of check this rigorously by picking some limit.
Thank you.
But yeah, so this matrix is essentially identity. But we, of course, in practice, we don't use this infinite kernel so much, at least not in machine learning, in other applications like Shepard's interpolation. But in machine learning, we use things like Laplace kernels. So they're not like that.
Hi, Professor Belkin. I have a question. So you gave the expected loss of simplicial interpolation as 1 plus 1 by 2 to the t times the base error, right? So what's the equivalent form for the 1 nearest neighbor classifier?
For nearest neighbor, it's just this.
Oh, so
for classification, for regression or something else.
And what happens? Do you know anything if we increase it to like 2 nearest neighbor, or if we increase the number of nearest neighbors?
Oh, so the loss goes down. So if you have very large number of nearest neighbors, you get close to base loss because you are averaging. The problem, of course, is that when you take a lot of nearest neighbors, right, in practice, you cannot take too many because that would be averaging over your whole data set, and that's meaningless. So, but in principle, given infinite amount of data, you can get consistency by just averaging over more and more nearest neighbors.
Thank you.
The thing is, of course, it's less interesting from our point of view because that goes further and further away from interpolation as you put more nearest neighbors. So somehow these schemes do something very similar to k-nearest neighbors, except they also interpolate. And we'll discuss this other side of interpolation because right now it's still not clear why interpolation may be a good thing. But actually, once you start looking at optimization, it becomes much more clear. And it may be that the real benefit is an optimization. I'm not. There is certainly a benefit in optimization. I'm not sure it's the main one, but we will see what it is. So maybe in practice, that's the reason that they work.
So also one question, like later when you spoke about the motivation of interpolating classifiers, and in one of the plots you had plotted this linear regression, right, with spiky, spikes near the data point. So there the assumption was that the noise is somewhat independent, right? It comes from a Gaussian distribution, it's somewhat independent. But if the noise had some structure, right, and so I can make this I can make the smoothing process go really bad, right? I mean, the smoothing process might just interpolate something else given that there is some structure in the noise. So what do you have to say about that?
Yeah, the structure of the noise is not so important. These results are kind of universal. So you will find the best predictor given enough data, assuming that they're very generic, like the noise has to be bounded and your underlying function has to be smooth enough. So it's pretty generic. It's not.
Okay.
It's not tied to a specific model to the noise.
For example, the adversarial noise is somewhat has a structure, right? I mean, you cannot add any noise to the image and it gives you some other label, right? There is some particular structure in the adversarial noise. So in that sense, like their smoothing might not help and some particular type of smoothing might help.
That's true, but that's because when we do predictions, we have a pretty think about what we use for this thing. So let's say something like convolutional neural network, right? That has a very specific structure built in the model. So there is some interaction between the things. This is kind of a generic. So here I have some sort of generic theory. This method will work given infinitely many data points, right? But this infinitely many, right? Maybe you need like 10 to the 100 data points, right? So if you want to cover this high dimensional space. If you have some extra structure, you can get away with far fewer data points, but you're paying something.
Okay.
Well, that's why convolutional neural network work better than for images than fully connected, right? Because there is no reason a priori that fully connected neural network will. They do work to images, but they're much worse because they don't have this extra in translation invariance.
Thank you.
Okay, maybe we can thank Misha again for a very thought-provoking lecture as previously. So we look forward to your future lectures, Misha, but I guess for now, the next thing is in about 8 minutes, the second symposium is going to start. So I will hopefully see you guys soon.
Thank you, Boris. Thanks, everyone.
Hi, Jeffrey. How are you doing?
Doing well. You hear me okay?
Yeah, we can hear you fine. We can see your slides.
Great.
So everything seems to be on track for now. That's always good.
Good. Yeah, I have a bad track record for technical difficulties with Zoom, so hopefully things go smoothly.
Okay. Well, you know, we can balance your bad track record against my surprisingly good track record. So hopefully, you know, I have a stronger weight in the nearest neighbor scheme. Yes, so far there haven't been any technical difficulties at the school, so that's good. You know, we'll just give people a minute or two to show up. Are you in Chicago at the moment, Jeffrey?
I'm in the Boston area.
Oh, Boston. Why do I think Chicago? You weren't in Chicago at any point in the last, like.
I barely set foot in Chicago, but
Okay.
yeah.
Okay. Well, nice. I will almost certainly be in Boston periodically this coming year. So that's exciting. I'll tell you when I come and if you're
cool.
around. Yep. Okay, let's slowly get started. So welcome back, everyone, to our second symposium, which I personally am very excited about. There's going to be a number of people who work in industry but work on theory. And I think that, you know, they're really good people to hear from because at least by physical proximity, they're maybe closer to people who do also practical things. So sometimes the influences can be slightly different, although sometimes the barriers are just as large. But okay, anyway, so our first speaker is Jeffrey Pennington. Let me just say a few words by way of introduction for him. And correct me if I'm wrong, Jeffrey. I just got this from the internet, so who knows? So Jeffrey got his PhD in physics from Stanford in 2013. Then he went on to do a postdoc in natural language processing and wrote a very influential paper with some of his colleagues there about what are called word embeddings, a specific algorithm called GloVe, which I checked has like 23,000 citations as of today, which is like, whoa. I don't know how often you check if you have a running clock on your wall or something, Jeffrey, but that's like, whoa, that's a lot of citations. I think it was maybe 2014. So that's pretty great. For the last, you know, quite a while, Jeffrey's been a research scientist at Google Brain. And, you know, I've enjoyed talking to Jeffrey periodically over the years. I always feel like I learned something. And so I imagine that this talk will be no different. And I'm excited to hear it. So take it away if you're ready, Jeffrey.
Great. Yeah. Thank you so much for the invitation. And yeah, I'm excited to speak today about some of the work I've been doing in collaboration with Ben Adlam, trying to basically shed some light on the so-called mysteries of deep learning through the lens of high-dimensional statistics. So the content of this talk will be kind of spread across two parts, the first of which I'll give now. After I speak, Ben will continue, and he will be building off of some of the mathematical tools that I'm going to present now to highlight more of the practical implications for machine learning. I hopefully will do a good job of setting the stage for him. And so to get started, excuse me, I'd like to discuss some background on backgrounds. So suppose that you ran a bunch of experiments and acquired some data that looked like this. And, you know, it's relatively clean, you know, it looks pretty nice, maybe you're happy with it. And you want to know if you've made a groundbreaking discovery. Well, clearly to answer that, you need to know well, I mean, what your prior expectations were. If you expected an upward trend, you might find this data to be pretty surprising. What if you expected a downward trend? Well, then the answer to this question maybe depends a bit more intricately on your understanding of the background. Well, what you expected to see if nothing interesting were happening at all. And you know, a thorough understanding of the background can actually help filter out really boring results. So here, if you have a very precise prediction of what you expect, maybe you look at this and you say, well, actually, this is just all in line with what I thought would happen. But if you're making very precise measurements and have a precise prediction for the background though, and you look closely here, you might think, there's maybe a little blip right there. Is that actually interesting? And with a very precise understanding of the background, maybe it is something interesting. So this is actually data from the ATLAS collaboration at the LHC at CERN in its search for the Higgs boson. And through decades of theoretical developments, understanding the experimental configuration and whatnot, researchers have developed very precise predictions for the background, and they have very good measurements of the signal. And you can subtract out the background. And this is actually the data that convinced the world that the Higgs boson exists. So this little blip was the discovery of a new fundamental particle. And so point I'd like to make is that, depending on how well you understand the background, you may be able to derive different conclusions from the same data. So in the context of machine learning, the argument I'd like to make in this talk is basically we need better backgrounds. And by way of example, I'd like to focus on the notion of double descent, which I'm sure you have been or will be hearing about during the course of this school. And anyway, if not, the description is quite clear and I think familiar to you in terms of intuitions if you have some experience training big models, namely that deep neural nets are very expressive and flexible class of functions. So here's a figure showing some image classification models. This is now a few years outdated, but even I guess 4 or 5 years ago, the top image classification models on ImageNet were leveraging hundreds of millions of parameters. That number is dwarfed by the state-of-the-art language models now, which have hundreds of billions or more parameters. So these are very expressive functions. And it's not just that they have lots of parameters, it's that they can fit really, they can fit anything. So if you, in a very, I think, convincing set of experiments from Zhang et al. A few years ago, you take a architecture that's been tuned for a particular class, image classification in this case, and you just swap out the data for some noise, noisy pixels, noisy labels, and you just ask what happens if you train that architecture on that data set. You find that you can easily memorize it. So this is potentially surprising because it suggests that you're far to the right. Your hypothesis space is huge. You're interpolating the training data. Standard wisdom suggests that you should be overfitting, that in the U-shaped generalization curve, which maybe you've seen, that highlights the bias variance trade-off of your predictive function, that if your hypothesis class is too big, the expectation might be that the variance of your predictive function would be large. As a consequence, your total error would be large, and you would actually do better with a smaller model. That's not what neural nets do. So by now, this is a well-established observation that if you have a small number of parameters, then you do see this standard U-shaped behavior. The test error goes down and goes back up as you increase the number of parameters. But as you pass a threshold, which is around the point where you can begin to memorize the training data, then the test error starts going back down, and often the best performing models are very far to the right, huge numbers of parameters. So this has been given a lot of attention lately. And the question I'd like to focus on is whether or not this is interesting. Are we observing some kind of signal here, or is it just that we don't understand the background well? So the goal of this talk is to build a better model of the background. And to do that, I would like to work in the high dimensional asymptotic regime. So let me define what I mean by that. And en route to a definition of the high dimensional asymptotics, let me just briefly mention some of the more standard asymptotics that typically appear in theoretical analyses of machine learning models. So the most standard kind of limit is the large data limit, where the number of samples n is going to infinity. You know, this is a standard paradigm in many analyses in statistical learning theory. Leverage this kind of limit. Results rely on uniform convergence of the empirical risk and whatnot. Common limit is the large data limit. More recently, and I think the content of many of the talks you're hearing about in the school is the large width limit, where you can actually show in certain circumstances that the neural nets in the large width limit behave like kernels, either from the Bayesian perspective like a Gaussian process, or under gradient descent, like by means of the neural tangent kernel. And I guess a natural question is, what happens if more than one of these numbers is large? So that's the focus of the high dimensional asymptotic regime that I think is actually very relevant for neural nets in practice, and the one that I think underlies a lot of the behavior in double descent and a lot of more interesting phenomena, some of which hopefully Ben will discuss after this. But the basic observation I think you can sort of summarize in this kind of cartoon sketch of how some typical models on typical data sets, how many features, samples, and hidden units they might have. So you could also add a column with the number of parameters, which could be relevant. But the basic point here is that, in certain circumstances, not all, but many, these numbers are all large and all comparable to one another. Maybe certain regimes have slightly different ratios, whatnot. But it's certainly plausible, I think, just by looking at these, that it might be important to consider the regime in which these numbers are all large and compare to one another. So with that in mind, we're going to focus on the high dimensional asymptotics. I'll be looking at 0 and 1 hidden layer networks, the asymptotics for which the dataset size and input dimensionality are going to infinity. And in the context of neural nets, also the case where the first hidden layer is going to infinity, all at the same rate. And I think it's these high dimensional asymptotics that really reveal some interesting behavior that's often missed in sort of standard asymptotic analysis. So by way of motivation for these asymptotics, probably many of you are familiar with the Marchenko-Pastur distribution. But for those of you who aren't, I think there's potential for a surprise in what can happen in distinguishing the low dimensional, the high dimensional regimes. So if you consider some data set X with n0 features and m samples, where each entry of this data matrix is independently drawn from a standard normal distribution. When the number of features is finite, but the number of samples is getting large, the covariance matrix converges to the identity, which makes sense, I think. In the high dimensional regime, actually, more interesting behavior can arise. So if n0, the number of features, is also going to infinity, such that n0 over n is constant, equaling phi, the limiting distribution of eigenvalues of that covariance matrix converges to a deterministic spectral density called the Marchenko-Pastur distribution. So you can imagine this as a sequence of histograms for increasing problem size. And the shape of that histogram converges to the shape of these curves asymptotically. So concretely, the y-axis is essentially the probability of drawing a given eigenvalue indexed on the x-axis if you were to sample an eigenvalue at random from the set of eigenvalues. So this is the limiting spectral distribution of the called the Marchenko-Pasteur distribution. And it just highlights that you can get some interesting, potentially counterintuitive behavior in the high dimensional regime. So by way of warm up, I'd like to discuss linear regression briefly in these high dimensional asymptotics, just to give you a feel for how things maybe differ from your intuitions, and also just to sort of set the stage for what's to come. So I'd like to consider linear regression, and I'd like to do so in a very simple setting where the covariates are IID Gaussian, and the labels Y are also IID Gaussian, independent of X. So trivial setting, you're just trying to memorize some noise. So here, gamma is a ridge regularization constant. And you can solve this problem by just looking for the values of W, which set the gradient to 0. W star turns out to just equal Y QX transpose. Q being the so-called resolvent of the data covariance. The resolvent is an important object that'll show up later in a variety of contexts. And here gamma, the ridge constant, shows up as the spectral argument of the resolvent, which we'll also come back to. The point here is that you have some explicit representation for the optimal weights in this simple ridge regression setting, which you can plug in to compute the training error. And if you expand the Frobenius norm is the trace of the argument times its transpose, and then expand the argument of the trace into the 3 additive terms, use the fact that Y is IID Gaussian, and use the definition of Q to replace X transpose X. A little algebra shows that the training error is expressible as the trace of Q squared, trace of the square of the resolvent. Furthermore, that can be written as the derivative of, with respect to the ridge constant of the trace of the resolvent. So actually, this is just one manifestation of the many ways in which this resolvent matrix and its trace show up in these high dimensional calculations in a fundamental way. So as a brief, quick aside, I just wanted to say a little bit about the Cauchy transform, which is the trace of the resolvent. This is an important object in random matrix theory in many ways. But on the right-hand side here is the trace of the resolvent of M. You can think of Z here as negative gamma. If you imagine moving to an eigenbasis of M and using the cyclicity of the trace, you can write this as an integral over the eigenvalues of M. And if you look at the integrand here, you see there's a pole anytime Z approaches the real axis on the support of the spectrum. And so it's, I think, intuitive that this Cauchy transform G is thereby capturing all the information about the eigenvalues through its sort of complex structure. And indeed, you can make that quite precise just using properties of the delta function, showing that you can essentially invert the Cauchy transform to recover the spectral density. So this sort of same information is encoded both ways, but this Cauchy transform, trace of the resolvent, can be quite useful thing to manipulate from the analytic and algebraic perspective. So coming back to the training error, as I mentioned, it depends on the trace of the resolvent matrix Q. And through the definition of this Cauchy transform, one can write it as an integral against the Marchenko-Pasteur distribution, which I showed you some plots of earlier. There's a simple algebraic formula one can integrate to obtain the Cauchy transform, which I wrote here. It's a function of phi, which is the ratio of the number of features to samples, sort of a kind of high dimensionality ratio, and of the spectral argument Z, which we're going to essentially evaluate at negative gamma, the ridge constant. Okay, so there's an explicit formula by using this, taking the derivative of that guy for the training error. This is not particularly interesting in any way other than to highlight that, you know, in these high dimensional asymptotics, you can get these essentially simple formulas for the limiting error. And you can see the dependence on the underlying parameters is made explicit. And what we'd like to do is to think about how we can generalize this to the test error so that we can say maybe some non-trivial things. But before we do that, we also need to move to a slightly less trivial model. So I'd like to introduce the concept of random feature kernel regression. So linear regression, being very simple, is easy to study, but it fails to exhibit one of the salient properties of real models, which is the ability to change the capacity of the model in a parametric way that's independent of the data distribution. So for neural networks, you can increase the number of neurons in a given layer, for example. But for linear regression, you can't really do that because the number of parameters is equal to the number of features. And there's ways you could try to get around this and whatnot, but I think the most natural way to generalize linear regression to a setting for which you can vary the capacity of the model independently of the data distribution is through random feature mapping. So basically all you do, I'm sure many of you are familiar with this, but for those who aren't, is you just take your data matrix X and you transform it by essentially a single layer of a fully connected neural net. So you multiply by some random matrix W, apply an element-wise nonlinearity little f, and that gives you a random feature matrix big F. And what you want to do is just perform linear regression on F instead of X. And this is random feature regression. It lets you model nonlinear functions of the data, and it allows you to vary the capacity of the model by essentially changing N1 here, the number of random features, or N1 in the context of neural nets would be the number of neurons in that first layer. There's some nice connection to neural net here if you think about only training the top layer. The result of that operation would be equivalent to solving the random feature kernel regression problem. And you know, the other motivating factor in choosing to study this model is that at least for certain simple data configurations, you can compute the test error exactly in the high dimensional asymptotics and thereby obtain insights high dimensional statistics can induce interesting phenomena that you might see when looking at the test error. So crucially, and to highlight again the high dimensional asymptotics I introduced before, we're going to consider the case where the number of features N0, the number of hidden units N1, the number of samples M are going to infinity at the same rate. So this is random feature kernel regression. And when the target vector Y is IID Gaussian independent of the labels, in the same setting we looked at for linear regression, essentially the same formula for linear regression follows, except you just replace X with replace X with F. Because again, it's just linear regression on these random features F. And the only difference here is that the resolvent is now not with respect to X transpose X, but with respect to F transpose F. And therefore the training error, as the derivative of the trace of the resolvent, requires knowledge of the Cauchy transform of this random feature kernel instead of the Cauchy transform of the Marchenko-Pasteur distribution. So how do we compute this guy? So there's a number of options. Just to give a very quick survey of a couple. A naive option, known as the method of moments, might be familiar to some of you, especially those of you who are following closely Shou and Dan's analysis of large width expansions, this sort of perturbative type approach is basically what the method of moments would do, expanding not in 1 over n, but in 1 over z for large z. You can expand the trace of this resolvent and try to evaluate the kth order term by essentially writing it in index form. You have a sum over a bunch of different ways of pairing indices of a string of products of entries of this random feature matrix. Without going into the details, because they're admittedly fairly horrendous, you can evaluate this to leading order and resum the series. And that's actually the first way we computed this Cauchy transform. It's not recommended. The recommended method is much simpler, is to leverage this concept of universality that many of you probably are aware of from random matrix theory and other disciplines as well. But in the context of RMT, the statement is something like, in many cases, you can replace the random matrix of interest by another one, so long as you preserve the low order moments. And if you do that, then the statistics of relevance that you might care about, for example, the distribution of eigenvalues or certain tracial objects, are also preserved asymptotically. So I won't have time to go into many details about this, but in our context, turns out there's a very nice way of obtaining a Gaussian equivalent for the nonlinear random feature matrix F, which basically linearizes this activation function little f in the sense that big F lin depends linearly on the argument Wx. And as you can imagine, there must be some dependence on the activation function in order for you to capture the low order moments. So those are captured through these Gaussian integrals, eta and zeta. There's also the addition of a independent random matrix A that comes in order to properly match the moments. And so this is kind of like a linear signal plus noise linearization. And essentially, what you do is you just replace F with F lin everywhere it shows up. And you might think, okay, well, that still looks terrible. How do I compute the Cauchy transform of F lin? And this is where some nice tools from free probability come into play. So I won't have time to go into a huge amount of detail, but I'd like to describe a little bit about free probability because I think it's quite elegant. It's basically an algebraic formalism that lets you add or multiply or otherwise manipulate so-called freely independent, non-commutative random variables. In our context, the random variables are the random matrices A, W, and X that characterize F lin. And we'd like to compute the Cauchy transform of F lin, because again, that's what lets us get at the training error and eventually the test error. I'll come back to that. And free probability is a way of manipulating the constituent Cauchy transforms in order to get the Cauchy transform of the combination. So I'd like to spend just a couple minutes talking about free probability. So free probability relies on a generalization of the concept of independence to the non-commutative setting. So there are many definitions of classical independence of random variables. One of them that generalizes most cleanly to the non-commutative setting of free independence is this one, where the statement is that X and Y are independent if for some suitable class of functions, say polynomials, that if the expectation of f of x, g of y vanishes whenever f and g have zero mean, in that case, then x and y are independent. And a nice generalization of this to the non-commutative setting just mandates that this happen not just for one product fg, but for a k-fold product of fg's. Admittedly, this is not super intuitive to me. It captures the non-commutativity in an intuitive way, I imagine. But a definition that I like better in the context of matrices which is slightly less precise, but is basically that the X and Y are freely independent if the entries in X and Y are themselves independent. And moreover, the eigenspaces of X and Y don't align in any particular way. So that additional constraint relates to the non-commutativity. And so why do we care about all of this? And it's because of the sort of the following algebraic properties. So in the context of commutative probability, if you want to add two random variables, an elegant way to do that is to lift the problem to the space of characteristic functions, essentially the Fourier transforming the probability distribution. Then addition of random variables is trivial. In a similar way, in the non-commutative context of free probability, there's an analog of characteristic function, and which are basically the R transform and S transform, which relate to the Cauchy transform through some functional equations. So here's an equation defining R in terms of G. You have to sort of invert this equation to get R. And the nice thing about this is that if you lift the problem to the space of R transforms, there's a kind of homomorphism of addition. So the R transforms are additive. And so the procedure is kind of given here. You take the constituent Cauchy transforms, get their R transforms through this equation, you add them, and then you kind of descend back down to the space of Cauchy transforms. There's a similar prescription for multiplication of random matrices called through the S transform. There's a slightly different functional equation defining the S transform, but the same idea. You lift to this space, multiply, and then descend back down. So I just want to give a quick example about how this might work in practice, just to give you, because it's fairly abstract at this level, just to give you a concrete sense of, kind of how easy it is to manipulate these things. So in this concrete example, I'll just look at the linear activation function case, for which fln is just W times X. And in the case where W and X are IID Gaussian random matrices, unless assume for simplicity that n0 equals n, so this high dimensionality ratio factor phi is 1. Then the expression for the Cauchy transform of W transpose W and X transpose X are actually the same. They're both the Marchenko-Pasteur distribution specialized to phi equals 1, which has a simple root of a quadratic equation. If you change variables to X, then you can write G of Z as X over 1 plus X. And the equation defining the S transform in terms of G then simplifies and gives you that S of X is just 1 over 1 plus X. So here's essentially the S transform of the Marchenko-Pasteur distribution. It's a function that takes X to 1 over 1 plus X. And that's the same for both W transpose W and X transpose X. And to compute the S transform of F transpose F, you can basically use properties related to the cyclicity of the trace and to kind of a homomorphism mapping multiplication into the space of S transforms to deduce that the S transform of F transpose F is 1 over 1 plus X squared. So you're just multiplying S transforms. And then you take this function, 1 over 1 plus X squared, plug it in to this functional equation that defines the S transform, and kind of go the other direction to pull out the Cauchy transform. So it turns out in this case that, that the Cauchy transform of the product W times X now obeys a cubic equation, which you can solve, and you get an explicit representation for the Cauchy transform, from which you could extract the spectral density if you wanted. So this is how things work. This is a simple case, but basically just some algebraic manipulations like this. that free probability enables you to add and multiply Cauchy transforms with random matrices that are free. Returning briefly to our setting where flin is not just W times X, but that quantity plus another random matrix. Same idea. You first compute the product, Wx, and then you get its R transform, and then you add that to A, and then that gives you flin. And from there, you can plug things in to get the training error by computing the derivative, just like we did for the case of linear regression. Okay, great. So that's all I want to say about free probability for now. And I would like to return to kernel ridge regression in high dimensions and talk about the test error.
So maybe can I interrupt you for a second, Jeffrey, with a general question then? So, maybe this is a good time if you have something like this, you have these two phi and psi parameters or whatever you call them. And, do you have a kind of simple intuitive picture before you show us the answer for how we're supposed to think about, the regimes, for example, when one is much smaller than the other, or one just degenerates to zero, or this kind of thing, just very roughly what we should expect, in one limit, we're supposed to get the old like number of data goes to infinity kind of thing, maybe, and so on.
Yeah, right. It's hard to keep track of everything in your head. So in green at the bottom is, again, the definition of the two ratios that are relevant in these asymptotics. N0 is the dimensionality of each sample and the number of samples. And N1, the number of random features. So in the limit that phi goes to 0, you should get the kind of large data limit. And indeed, if you look at the distribution, the Marchenko-Pasteur distribution, when phi goes to 0, you see in the sequence from blue to purple that the spectral density is kind of collapsing more and more towards a delta function at 1, which is what you would get if the covariance converged to the identity. So one limit of relevance is phi goes to 0, which gives you the large data regime. And the other limit of interest is psi goes to 0, where N1 is going to infinity faster than anything else. That limit gives you essentially the large width regime, where you get a deterministic constant kernel described by neural net Gaussian process, for example, or in a related context, the NTK. So yes, to answer your question directly, phi goes to 0 is a large data, psi goes to 0 is a large width.
Thanks, Jeffrey.
So I haven't shown you any formulas that contain phi and psi that those limits might be useful for interpreting, but perhaps we can say a little more later. Returning to the question of kernel ridge regression in high dimensions, we talked about the training error. Of course, the interesting question is the test error. And for that, it's important not to simply consider labels that are independent of the covariates. Then the test error is too boring. The next simplest thing you can do is a linear function of the covariates. So that's what we're going to do here. Epsilon is additive noise. Beta is a coefficient vector, which for simplicity we'll assume is isotropic and random. Variance 1, independent entries. And we'd like to compute the test error. So the way to do that is to consider some unseen point x tilde, and you pass it through your random feature map to get little f tilde, and you have some targets for that test point y tilde. And then you compute the squared error using your predictive using your predictive function w star, the w star times f tilde. And using the same idea as before, in the training error, you write the Frobenius norm as the product of its argument times its transpose and expand that out into 3 terms. But unlike before, it's not clear how to proceed because these terms now have complicated dependence on the random matrices in question. In particular, it's complicated by the fact that Q, which is a matrix inverse of an object that depends on the random matrices W and X and F, you have these guys showing up inside of this inverse and sort of in multiplying them in the kind of numerator. And that really complicates things. So I'm not going to go into a huge amount of detail here, but the idea is you use these universality, this concept of Gaussian equivalence, to replace both the training random feature matrix F by Flin and also the test. And then there's a bunch of kind of random variables for which the expectations are trivial because they don't show up inside the resolvent. So there's no inversion and it's just trivial, either linear or quadratic functions of those, which you can compute, or basically all concentrate. And so after you do that and collect terms, what happens is you get rid of everything except for W, X, and this additive noise matrix A that comes into the linearization. And you have a combination of quadratic and linear terms in the resolvent. And the details aren't super important other than the fact that what you need to do is evaluate asymptotic traces of essentially rational functions of random matrices. And unfortunately, since I'm running low on time and because it's way too complicated, I'll just give you the answer, which is there's a nice generalization of the theory of free probability to a slightly more useful context, in this case known as operator valued free probability, which you can read more about in our papers, also a great book by Roland Speicher on the topic. And I encourage you to check those resources out to see more details about how we do this. But the basic idea is you use some concepts related to free probability to compute these asymptotic traces. You can characterize the limiting test error in terms of what ends up being roots of a coupled polynomial system. Here, phi and psi show up. It's not easy to deduce the limiting behavior by staring at these equations. But what you would do is carefully take the limit that phi goes to 0 to get the large data regime, or psi goes to 0 to get the large width regime. And indeed, you get the behavior you expect in those limits. But in the case where those constants are not going to 0, you can evaluate those formulas and you get exactly the qualitative behavior of double descent. So here is the test error and training error, training in dotted lines, test in solid lines, plotted against the over-parameterization ratio, the number of random features divided by the number of samples. The colors are different strengths of the ridge regularization. And you can see that you get this peak near the interpolation threshold. You get the double descent behavior. The best performing models are out for large width. And I just remind you that this is occurring in the context of completely unstructured random feature maps. Nothing interesting happening on the model side, no structure, nothing. The data is isotropic, unstructured random Gaussian data, a completely trivial target function. And so I would say that the conclusion here is that in high dimensions, double descent is a background, not the signal. And that if you're training a neural net in high dimensions and you see double descent, that's expected. And if there's something interesting happening, you should think about subtracting the background and seeing what features your model shows on top of this sort of expected behavior before trying to draw conclusions. So that's all I have. And I'll go ahead and stop there, I guess.
Okay, let's thank Jeffrey. We have a couple minutes for questions. So if anyone has questions, please go ahead. Otherwise, I will ask some questions probably.
I have a question. So you mentioned that for basic linear regression, there is no double descent. But I think I have observed and also maybe tried that you can, like for random inputs and random outputs, you can still see a double descent, although you don't really have to like a curve like this, but more like like if the test error shoots up at this ratio, right?
You're absolutely right that you can see a peak like this and literally a double descent in the test loss. It's linear regression. Those were the first class of models people studied and found the behavior there in many contexts. No, I'm not saying that it doesn't exist. I'm saying that the interpretation is harder because inevitably when you change the number of parameters in the model by one mechanism or another, you're essentially changing something about the data distribution. And so you've coupled a change to the data distribution with a change to the model. And I believe that's unavoidable in the case of linear regression. And for that reason, I think it's important to study the random feature models or some model for which you have a knob to control the model complexity that leaves the data distribution unchanged.
I see. Thanks.
Hi, I also have a question. So what were the conditions on the activation function F to get these like free probability results?
Yeah, I mean, I'm not sure what necessarily the absolute minimal conditions are, but if you just kind of need the moments to exist. So you want it and its derivative to not be pathological. So something like 1 over x, f of x is 1 over x, or something worse than that, could potentially be problematic. But common activation functions that anyone uses certainly fit the bill.
And then I guess I have another question. So here we're assuming that W and X are independent, completely independent of each other. And so just maybe someone who doesn't have a lot of experience in machine learning, is there interest in like, if they were dependent on each other, is that an interesting question? Because there's been some recent random matrix results on sort of like an elliptic version of the Marchenko-Pasteur where they're not like, it's not X transpose, it's like X and Y where they're dependent, and then you get like a fattening in the complex plane of the Marchenko-Pasteur. So you would already have, you could get the Cauchy distribution of the, singular value distribution. Is that interesting, or is that just not applicable?
I mean, certainly in the case of training a real model with gradient descent, your first weight matrix will inevitably begin depending on the data in a complicated way. But if one had a heuristic for modeling that, I could see it being an interesting direction to pursue. I guess our perspective here was more what one could say in the simplest possible setting, which seems to be enough to capture the main empirical phenomena, but certainly trying to generalize things to capture more closely the realistic training procedures and dependencies induced by that could be a fun direction to pursue. We haven't done it.
Thank you.
Okay, since we're a little bit over time, maybe we can thank Jeffrey again for a very instructive talk. Thanks, Jeffrey. Every time someone says double descent, I'll just say that's background from now on. And they won't know what I mean unless they were at the summer school, but that's okay. So when you get a second, I think you're still here, Ben. Go ahead and share your screen. I think you can. I think.
Yes. Okay, let me know if that comes through.
Yes, I can see it and we can hear you. So this is all great. Okay, so let me very quickly introduce Ben before we get into his talk. Okay, and as I tell everyone, correct me if I'm wrong, because I just get this information from random places on the internet. Okay, so Ben got his PhD in math from Harvard in 2017. Is that right, Ben? Or was it 2018? Okay, I wasn't sure how that aligned with your residency. Okay, 2018. And I guess working on random matrix theory related stuff. And then basically since then, he's been a research scientist at Google Brain, more or less. And, so Jeffrey and Ben have written this series of papers on triple descent and high dimensional statistics for for random matrix problems related to neural networks and various linearizations of neural networks, which I found to be like very instructive. And so I imagine that he'll continue talking in that general direction. And so I'm excited to hear the latest and greatest, but also the digest. Those papers can be sometimes brutal, depending on which part of the calculation you're trying to follow. So go ahead, Ben, please.
Sure. Okay. Thank you for the introduction, Boris, and for inviting me to talk. I would just try and pick up from where Jeffrey left off, basically, and talk more about the machine learning implications of some of the calculations we've been doing. So just continuing this theme of trying to separate which phenomena are unique to deep learning and not simply a consequence of high-dimensional statistics. So we have some kind of candidate phenomena for this. One is this idea of benign overfitting, which you can kind of characterize by two things, I would say. So I think Jeffrey had this plot now, and it's kind of amazing that even though this is 5 years ago, we have 3 orders of magnitude more parameters in our biggest models these days. And this is why I actually got interested in deep learning, was I just couldn't believe that you could fit a model with so many parameters and have it generalized. It kind of ran counter to everything I knew about machine learning. So that's amazing in itself. But above and beyond that is this idea that it's also the optimal thing to do to have a heavily parameterized model, that you can actually do the best in terms of your test error by just using a really large model.
Ben?
And then there's this idea of...
Hold on, Ben, your audio is coming through kind of staticky. You sound like a robot. I assume the pandemic hasn't been that.
Okay, let me try... is this any better?
I'll try that again.
Is this microphone better?
It's different.
Not really. Okay. Let me see.
I mean, it's okay. We can still more or less hear you, but if you take 1 minute to resolve it, it might save all of our ears. But if not, we'll listen as is.
Okay. Yeah. Let me just try this. Sorry, we don't really use Zoom at Google, so this is my first time doing a presentation of Zoom. Okay, let me try joining the meeting with my iPad.
Okay, sounds great.
Okay, is that audio better?
Yeah, that's great, actually.
Okay, and maybe I'll... Okay, so hopefully this sounds better now. Okay,
yeah,
so you've probably heard a lot about double descent in the summer school already, and Jeffrey mentioned it, but it's just this idea that there's a parameterization, there's a regime when you go into very over-parameterized models that we didn't really know about before, I think. And to talk about some more recent phenomenon, I would suggest this idea that if you want your model not just to be good on a test distribution, which is the same as the training distribution, so you make it robust to small changes in the distribution of the data, you should actually use an over-parameterized model too. And the best thing you can do is make that model very large. And to make this more precise, you could make a scatter plot where you take the accuracy of your model on the distribution that is the same as the distribution the training data were drawn from, and you calculate its accuracy on a shifted distribution. So now this distribution is slightly different than the original one. I have 2 accuracies for a group of models, and I could just plot a scatter plot of those accuracies and fit a line to that. And what you see is a very linear behavior. So this kind of makes precise that idea of why bigger models might be more robust, right? So we use larger models, that improves the regular accuracy and also therefore the robustness. So these are interesting phenomenons, how unique are they to deep learning? And we have this idea of using random feature models as a kind of null model, and to look at whether we can replicate these phenomena with a simple, random feature model that no one would argue has anything to do with AGI or anything like that. Okay, so here are the advantages of random feature regression in high dimensions as a model. I think Jeffrey sort of covered most of these. And I just want to emphasize this strength again, that you can change the parameterization of your model in a kind of easy way without changing the data distribution, that you can run the whole gamut of under-parameterized to over-parameterized. And often our plots will have that as their x-axis. Some disadvantages and things that we won't be able to capture with random features are that there's no feature learning, right? These are just sampled randomly. The optimization is very simple for random features, right? So you can state that the predictive function is the solution to some optimization problem, but it's not terribly interesting because you can just solve this problem in closed form. So we won't, talk about any of the implicit regularizing effects some people argue SGD has, for example, and we'll just focus on really simple architectures. So single hidden layer neural networks. It's possible to imagine doing these kind of analyses for more complicated architectures, but the difficulty of the computation sort of go up in a corresponding manner. Okay, so I'm going to take these phenomena in pairs and talk first about the double descent and benign overfitting issues. So here is just a reminder of the random feature model that we'll be studying. So we're defining a very simple distribution for how the data are generated, right? The results that we get will not be distribution independent as they are in classical statistical learning theory, right? We're analyzing a really specific problem here. And you should recall that these dimension parameters are all becoming large, right? So this is a distinct limit than both the large width limit and the classical statistical learning theory limit, in the sense that we're defining a sequence of problems, right? The data set is increasing, and the dimensionality of the data and the model is increasing in the same limit. So we're looking at a new asymptotics, and the argument is that this limit is more descriptive of what happens in practice, right? So I think the setup can seem strange at the beginning, but the real idea is just that by looking at this limit, we actually replicate some of these interesting phenomena. Just to remind you about the random feature model and the predictive function for that model, here are just a couple bullet points. The key assumptions here are the high dimensional assumptions, that these dimension parameters are all becoming large and their ratios are converging to these two constants, phi and psi. And there are some technical assumptions on the activation function, which I think Andrew asked about. So we're assuming that the activation function is differentiable almost everywhere. And this assumption about the growth of the activation function is kind of sufficient for the moments to exist in a way that allows us to control the quantities that we need in the calculation. So these are pretty standard assumptions for concentration of the random matrices. And I think the first paper to really demonstrate the power of this random feature model was May and Montanari's paper from 2019, where they really showed that you could replicate the important features of the double descent behavior. So I think Jeffrey had a plot like this right at the end of his talk. But the important features here are you have this U-shaped bias variance trade-off in the underparameterized regime. And then after the interpolation threshold, the test error starts to come down again, and we find the optimal performance in the heavily overparameterized regime. And this model also showed that high SNR was a necessary component for the optimal performance being in the overparameterized regime. So what I want to do is kind of dig into this double descent behavior a little bit more and ask about the causes of double descent. And specifically what that means is analyzing the model's bias and variance as it goes through this transition of double descent. And to sort of set the stage for that, here are some kind of intuitions we might have about bias and variance, and to motivate why we should care about those things. So bias is roughly measuring how the model class is able to capture the data, right? And by adding random features, we will increase the complexity of the model class. So we would expect a kind of monotonic behavior in the bias. The more parameterization we have, the lower the bias. That's kind of complicated in other models by this issue of how you choose the predictive function from the model class, right? So I mentioned these issues of implicit regularization and stochastic gradient descent. We're kind of putting all of those to the side here, and you know, we can kind of ignore those issues around implicit regularizations. And then for the variance, it's directly relative. It's directly relevant to you if you care about model robustness. So one thing it's telling you is how your predictive function could have been different, right? If I had got slightly different data, or you know, my parameters were initialized differently, how much does my predictive function change? So it's telling you how much you should believe the predictions from a single run of your training process. So it's relevant directly for kind of robustness reasons. And it's also relevant technically, right? Because it is a measurement of the sensitivity of your algorithm to its inputs. So, and I mean inputs in a very broad sense. So the random seeds that you use, the particular data, even things like the ordering of your mini batches in stochastic gradient descent can have a big effect on the ultimate predictive function that your algorithm produces. And when you're able to control the sensitivity of your algorithm, that's exactly the ingredient to these classical statistical learning theory generalization bounds, right? You want to show that the output of your algorithm wasn't too dependent on the particular sample of training data that you've got. And that kind of concentration argument is exactly what feeds into generalization bounds. Okay, so I want to briefly talk about the bias variance, about bias and variance from the definitions, because I think this is something that I'm sure everyone has seen, but there is a lot of subtlety there that comes out when you start to look more closely. So the first thing to note is that this is conditional on a point X in your input space. That's how this decomposition starts. So we're looking at the loss. Obviously, this is a regression problem, so squared error makes a lot of sense here. There are kind of other versions of this for different types of loss, but we'll just focus on squared error. And we're asking about, if we rerun our algorithm, on average, what do we expect the loss on a single point X to be like when we compare the true label Y of X to our prediction at X from the training process? And what we see is that just by expanding this and canceling the cross terms out, we get three different terms. The first is called the irreducible error, or the Bayes error. And that's basically how much the label at X varies. So this is a property of the data distribution. There isn't really much we can do about it. It will just be determined by the distribution the data are sampled from. So it's often ignored, and I'll kind of ignore it from here on and just assume that on the test points, there is no label noise. So we'll just remove any randomness in Y of X. And you can think about just subtracting that out if you prefer, because it will just add a constant to the error. The next term is the bias. So this is comparing the average label at X to the average prediction at X. And it's measuring their difference in the same loss that we had on the left-hand side, right? The squared error is what it's measuring. And that's the bias at X. And then we have the variance term, which is measuring how much the predictive function changes at X after we rerun the training algorithm several times. And what we can do then is we can average over this point X when we draw it from a particular distribution. So normally you would consider X sampled from the same distribution as the training set, right? That's your sort of unshifted test error. But this could be done for any distribution. So sometimes I'll talk later about the test distribution being different, but the bias variance decomposition is not really assuming anything about the test distribution. And then ultimately we get these two terms, which we'll call bias and variance. But I've been kind of deliberately vague about how these expectations, these inner expectations, the ones in the top line here, are defined, right? So I kind of leaned on this frequentist notion of saying rerunning the training process without actually giving you the random variables. These expectations are over. And that is a big part of the subtlety of this decomposition. So one approach to this would be something I'll call the semi-classical approach, which is to just do the bias variance decomposition with respect to the label noise on the training distribution, or on the training set, sorry. So we have label noise on the training points, and those random variables is what we're going to take expectations of in the inner part of our bias variance decomposition. And if we do that, we have some randomness left, right? So we'd have to condition on the training points and the weight matrix W that is used to generate the random features. And there are a couple of options here, right? So one thing that is kind of natural is just to average over them when you average over the test point, right? The order of the outer expectations is not so important. But then we get a bias and a variance, which I'll call bias semi-classical and variance semi-classical. And this is kind of the approach taken in May and Montanari's paper. They don't explicitly take these expectations, they just treat these bias and variance terms as random variables. But because they converge to their expectations, this is effectively what is computed there. And what you see is very surprising. So the variance kind of behaves in a way you might expect and diverges at the interpolation threshold. But the bias does too, and it's non-monotonic, which is really breaking that intuition that I described earlier. So what is happening here? Can we give a more detailed explanation for this behavior? So an alternate approach would be to, instead of just take the inner expectations with respect to label noise, include all sources of randomness that your training process has, so all its inputs. And in the case of random feature regression, that would be the weight matrix W and your input points X. And if you do that, you get a different decomposition, which I've just written here, that you can then average over your test set. And you get two terms, bias and variance. I'll just call them B and B. But this is fundamentally a kind of multivariate approach in that it pushes all the randomness into these terms. So the immediate question that you might have from this is, variance is kind of measuring sensitivity of the algorithm to its inputs. Can we do any kind of credit attribution that says, actually the variance is caused by the weights or is caused by the training data, right? How can we decompose this variance and split it up into interpretable terms? And a natural first step to this might be to apply the law of total variance. So here, we're just splitting the variance of a random variable y into two terms. This is sometimes called the in-group and the out-group variance. The term on the far right here is kind of the variance explained by x, the variance in y explained by x. And the reason for that is it marginalizes out everything that is not x, right? So you condition on x, all the other random variables in the probability space are marginalized out, and then we just look at the residual variance that is left. And that therefore is explained by x. So could we do this in our situation? What would we condition on, right? So we could condition on the data or the parameters, or we could condition on the labels, or there are lots of choices here. And the issue is, depending on what we choose to condition on, we'll get different variance decompositions. So one approach taken in Neil et al.'s paper from 2018 was to condition on the data. So we get two variance terms. And the first one here, VD, we could kind of interpret that as the variance explained by the data for exactly this reason that I just mentioned. And then there's this other term, VD complement, and that we might be tempted to interpret as the variance explained by the parameters, right? Because what else is left, right? We've got the variance explained by the data, so this must be the variance due to the parameters, right? So with these terms, we can exactly perform the kind of calculations that Jeffrey was talking about and just say asymptotically how they behave in this random feature model. And so I'm just plotting that here as a function of the number of parameters relative to the data set, the training data size. And now taking this multivariate approach, the bias kind of behaves as we would expect. It just decays monotonically with the parameterization. And we have two variance terms. One seems to be diverging at the interpolation threshold. That's the VD complement term. Sorry, I'm having audio problems.
I don't know what it's caused by, Ben, but sometimes you have to actually totally disconnect your audio when you use two different Zoom sessions.
Okay. Sorry, I have the audio back now. Okay, sorry about that. Right, so the variance term that's diverging here is this one that we were tempted to interpret as the variance due to the parameters. And you could kind of corroborate this observation that the double descent behavior is caused by the parameters by doing an ensembling experiment. So by generating an ensemble of random feature models where you generate many different independent samples of random features and train them on the same training data and then average the predictions and compute the test error of that method, you would see this double descent behavior vanish if you had an infinitely large ensemble. So that kind of suggests that, again, that this variance explosion at the interpolation threshold is really caused by the parameters. A kind of different approach here would be to condition on the parameters rather than the data. And there was no real reason we chose the data previously. And if we do that, we get a different decomposition for variance. I'll call these terms VP and VP complement. So here we would interpret the first term as the variance explained by the parameters. And then the second term is just whatever is left. And we might call that the variance explained by the data. I'll label it VP complement. And we reached exactly the opposite conclusion. So now the term due to the data is diverging at the interpolation threshold. And we could do an ensembling experiment here and find exactly the same. Oh, God. Sorry. Was I muted or is it okay?
No, you're okay, Ben.
Okay, sorry. Right, so you could do an ensembling experiment where you're resampling the data but using the same random features. And again, that would remove the double descent behavior. So you've kind of reached this opposite conclusion, right? Just by the random, or just because of the order of the conditioning in this variance decomposition. So how do we resolve this paradox? Well, the first thing to do is note that this variance explained function is super additive. So, what this equation is saying is that if I take the variance explained by x and I add to that the variance explained by x2, then that will be less than or equal to the variance explained by x1 and x2 together, right? And that kind of motivates this following equation, which is very, very simple. But the important thing here is that we get 4 terms and all of them are non-negative. So we have like the variance explained by x1, the variance explained by x2, and then this kind of term in the parentheses, which is the variance that x1 and x2 explain together in addition to what they explain individually. And that's really the key step to kind of unravel this thing. The final term here is just whatever's left. So maybe x1 and x2 are y is not deterministic conditional on x1 and x2. So there could be randomness that's left over. And you can generalize this to any conditioning number of random variables. And if you just make some stipulations that your decomposition of variance is symmetric and it has this subset sum relationship, which I won't talk too much about, but it's just related to this idea of marginalization, then the variance decomposition is unique. And if you were to just take the two variable case, these are the expressions that you get for the variance terms that will sum to give the total variance. And this is the bivariate version, but you can do a kind of trivariate version and you'll get 7 terms. This might look familiar. This is basically ANOVA. But one way to interpret ANOVA and what it's actually saying is just a generalization of the law of total variance, right, to any number of conditioning random variables. ANOVA kind of comes along with these other methods for kind of estimating these variance terms under some normality assumptions, but this is just one way to think about it, as a way to break up variance in a symmetric fashion. So let's, or I should say one other thing just to illustrate the diagrams that I'll show. Because the variance is a non-negative quantity, it's tempting to think about it as an area, and then these variance terms as partitioning an area, right? I won't really try and explain these too much. I think it's better to just see the examples, and hopefully it will become clearer. So let's look at our first variance decomposition from Neal et al. So what is happening here? Can we write these variance terms in more atomic fashion with this trivariate decomposition? Well, what you do, if you do that, what you see is that the complement term is actually the sum of 4 other variance terms. And it kind of partitions this Venn diagram in the following way. So that there's this top circle here is the complement term, and the bottom one here is the variance due to the data, explained by the data. So with the other ordering of conditioning, we get a different decomposition. And basically what's happened here is this term in the intersection of the Venn diagram is flipped back and forth. And we can sort of resolve the paradox by looking at this bivariate decomposition and seeing actually what diverges at the interpolation threshold is this interior term, the VPD term. So it's really the interaction of the parameters and the data which causes the double descent behavior. Either one on their own doesn't just explain it. But sort of marginalizing either the parameters or the data will basically reduce the variance term that will reduce any variance term in which the data or the parameters are involved. So if we marginalize over parameters, this whole upper circle here is actually reduced. So that's why we see these kind of results in ensembling experiments. And then just to say something briefly about May and Montanari's approach here, if you look at their decomposition in our trivariate terms, you see that their bias term actually includes some of the variance terms that we identify. And it's basically these 2 inner terms here which are diverging at the interpolation threshold. And this guy here will cause the bias to diverge, whereas this one here will cause the variance to diverge.
Ben, can I ask you a quick question?
Yeah, sure.
So actually go back one slide, maybe, I think is what I want to ask.
Sure.
Yeah, that one, exactly. So maybe you already said it, but I kind of didn't catch it or something. But I mean, it's interesting that it's only the VDP term that blows up at the interpolation threshold. And do you have a kind of, at least looking back, reason to explain that intuitively? Like could you?
Sorry, there's a bit of a delay in my audio as well. So, but okay. So to answer your question, I think this is pretty generic of nonlinear functions. So you can look at simple functions of random variables, for example, x1, x2 squared. And I think even in cases like that, the interaction term is kind of the dominant one. So it's to do with the nonlinearity. What is interesting is that from kind of preliminary experiments in real neural networks, it also seems to be true of real models. So this could be an advantage, right? Like it tells you that just by dealing with the uncertainty in a few of the inputs to your algorithm, you can get a lot of variance reduction. But I don't have a priori, like a good reason that the interaction term is the dominant one other than this non-linearity.
I see. Yeah, that's very interesting somehow. Thanks.
Great. Yeah, thank you for the question. Okay. So let me just show you the full trivariate decomposition. There are a lot of terms here. The checkerboard ones are exactly 0 in this model. And what we really identify then are these two variance terms here, VPX and VPX epsilon, both of which are causing the double descent behavior. And it allows us to resolve one of the open questions about double descent of whether it is caused by label noise. So if there's no label noise, all the terms that have a epsilon subscript will be exactly 0. So you can still get double descent behavior exactly because this VPX term is going to undergo double descent regardless of the label noise. But if you do have label noise on your training set, the double descent can be exacerbated by this central term here, VPX epsilon. So we thought that was a kind of interesting finding of going through this calculation. And here is just the kind of full picture together that allows you to sort of piece everything together. Okay, so in the time I have left, I'll try and talk about the distribution shift work, but maybe I'll just ask if there are any questions about the bias variance decomposition first.
I have a question. So do you also, I assume you're also getting some asymptotic forms of each of these variance terms. Is there something to be gained or some insights to be learned from them?
So basically everything I'm plotting here is the result of an asymptotic computation of these variance terms, right? So the interesting thing is you can define them for any model. The definition makes sense and the decomposition makes sense for any random variables, but usually in a neural network you would never be able to calculate the variance terms exactly. You might be able to estimate them, but the random feature model, it really allows you to predict these terms asymptotically. So that's what I'm plotting here. I mean, maybe that you're asking something about how the particular expression of those variance terms might be useful. And I think there are certain things you can do, like expanding these terms and looking at their monotonicity properties. I mean, something that's interesting, for example, here and kind of intuitive, is that if you look at the terms which are decaying to 0, they're all the terms that are associated to the parameters, right? And that's because in this limit where we have infinitely many random features, we're converging to a deterministic kernel, just because of the law of large numbers. So those terms will go to 0 because there's no variance associated to them anymore. So there are kind of interesting properties like that, which are intuitive and you can read off from the expressions for the variance terms.
I see. Thanks a lot.
Okay.
I have also one quick question.
Sure.
So can you split these two exploding terms, or is that the same thing as in like triple descent or these other papers? I mean, can you split them spatially in a way?
Yeah, that's interesting. So I don't know if there's a reason sort of a priori that they should diverge at the same point in the overparameterization spectrum. It seems that they do for this random feature regression, but I could imagine that that's not necessarily the case for all models. I don't think you can separate the divergences in this model though.
Okay.
Is that what you were asking?
Yeah, it was. Okay. Thanks.
Great, thank you for the question. Okay, so this will be quite quick, and I apologize, but I'll try to get through it. So I just want to mention some of these phenomena around distribution shifts. So in practice, distribution shift is the only thing that happens, right? This idea that the training distribution is exactly the same as the distribution of data that you encounter during deployment is just never the case. And it's a very wide class of phenomena, right? So all it means is that the training distribution and the test distribution are different. The distributions those things are sampled from are different. So it's an interesting project to kind of give mathematical definitions to types of shift, synthetic examples of those shifts, and particular data sets where that shift happens. And the kind of classical approach to this would be to assume maybe a metric on distributions and assume that the shift is not too big in that metric. And with that, control the change in the test error. But we're not going to talk about that. We're going to use this random matrix theory approach where we are exactly defining a data generating process. And we're going to define a way to shift that distribution too. So our particular type of shift is covariate shift, where the input distribution changes, but the conditional distributions of the labels remain fixed. And to just point out how the data distribution from before has changed, the training data are now sampled from a multivariate normal, but with some covariance matrix, sigma, and the test data are sampled from a different multivariate normal with a covariance matrix, sigma star. But that's the only change. And the random feature model is identical. Now, it turns out that a sort of important quantity that you need for this analysis is something that we call the overlap coefficients. So this is just the result of projecting sigma star onto the eigendirections of sigma. So the V's are eigenvectors and the lambdas are eigenvalues, and the star just denotes whether it's from sigma star or sigma. And if there were no shift, right, if sigma star were equal to sigma, what you would get here is that the RIs are exactly the lambda i's. So that kind of describes what we're measuring, right? We're measuring the weights of the different eigendirections in sigma star. And we have this technical assumption, which is necessary for the random matrix theory analysis. I won't really say too much about this. It's basically just a way of characterizing what the limiting behavior of the shift is through a convergence and distribution of this measure. Yeah, I mean, maybe the important thing to just point out is that this limiting measure mu is a joint distribution over lambda and r, which are roughly the spectral, roughly the eigenvalues of sigma and the overlap coefficients in this kind of limit of high dimensions. And we'll just assume this conditional expectation exists. So if we do that, here's an example of a type of shift, something we call the diatomic distribution. And that's just putting 2 point masses, one at alpha and one over alpha, and normalizing those, the weights of those so that the expectation is 1. And then we shift those by just raising alpha to this power theta, or 1 over alpha to theta 2. So this type of shift is the limit of a really simple definition for sigma and sigma star. It's just putting a certain number of eigenvalues at alpha and some at alpha to the -1. And then again, the shift is just a normalized version of the power of sigma. And to kind of motivate this analysis of the test error here, if you just consider linear regression rather than random feature regression, what you find is this expression for the test error under shift. And the key part here is just that you find these ratios of the overlap coefficients to the eigenvalues lambda. And a question you might ask is, what makes a shift hard or easy? If I have 2 shifts, is there anything that lets me determine which shift is harder than another shift? And there's a condition to do that based on the kind of monotonicity of this shift. So if we look at the ratio of the overlap coefficients and assume this is non-increasing, then we can basically prove something about how the test errors are ordered. The proof of that is very simple. It's just basically one line. But it kind of motivates the general definition of shift hardness. So here we're just generalizing that monotonicity condition, but with the conditional expectation. It's not like obvious to see how that generalizes it, but if you follow through the calculations, you can do that. And here are just very briefly some of the results that we find. Basically, we get a lot of monotonicity results with respect to different things. So one of the things I wanted to talk about in the second part of the talk was just how bigger models are actually more robust. So I'm plotting a contour plot here of total error, bias, and variance for this model with respect to the parameterization on the x-axis and the shift power. So this just is theta parameter on the y-axis. So we're getting more over-parameterized as we go from left to right on the x-axis, and the shift is getting harder as we go from large Y, 3 here, down to minus 3 here. So these shifts are hard and these shifts are easier. And what you find is that the bias, variance, and total error all behave monotonically under some conditions with respect to the shift difficulty. So the harder the shift, the larger the total error. And we also see some of the benefits of over-parameterization. So as long as we're over-parameterized, actually the bias and the variance will decrease as we add more random features. So this is exactly getting at that notion that it's not just in neural networks that bigger models can be more robust. And then very, very quickly now, I'll just say we are also able to replicate this phenomenon of linear trends in test accuracy. So I'm plotting the unshifted error versus the shifted error here for 2 different shifts. One is hard and one is easy. And we get this linear behavior by changing the number of random features. And on the right here, we're taking data from these papers where they evaluate ImageNet classifiers on 2 different test sets. One of these shifts is easy, namely the top images shift. And that's kind of illustrated by the fact that it's actually above the x equals y line. And the other shift, ImageNet V2 gray, is hard. And you can see these linear trends and the pictures are very similar. So I think that's basically all I have time for. I don't want to run into the next speaker's time. I realize I was very quick, but if anyone has questions, I'd love to follow up with them afterward, maybe.
Okay, yeah, thanks a lot for the very interesting talk, Ben. In fact, both your and Jeffrey's talks complemented each other obviously very nicely. So we appreciate that. And yeah, I definitely encourage any student interested to reach out to Ben, let's say by email or just by chat here or, whatever. This is meant to be a school. So this is meant to be a school. Sorry, I think I just cut out. This is, Ben will have at least hopefully some time to answer questions, but let us go on to the next speaker. I think Carolina's here. If she is, maybe
I am here, but it turns out I need to update my permissions to share the screen. Sorry, just a 1 minute delay.
Yeah,
I
no
actually need to
problem.
log in apparently, so I'll be back in 10 seconds.
Okay, great. In the meantime, I hope you all are enjoying the summer school so far. I know I am, but okay, I'm the one that constructed it, so almost by definition, I'm enjoying it, That's how that works. Yeah, 2 more speakers today, and then just as a brief reminder, the weekend is off. Hopefully it's a good time to review some materials from the lectures or whatever one does on the weekend. Okay, Caroline is back. Let's see. Oh, I think I need to make you co-host maybe on this new thing. Okay. All right, let's try that. Okay, success. We can see your screen. All right, very good. Very good. Wow, you have so many collaborators. That's good. That's a good sign. I'm not sure if I know that many people, you know. Okay, I'm kidding, of course. All right, let's see if I can find my information, which I took down about you. Okay, like I tell all the speakers, you should correct me if I'm wrong, because they didn't actually run it by anybody. Okay, so first of all, Carolina is someone who got a PhD in machine learning, technically in machine learning, right? That's the...
It was actually an engineering department, but I did do a machine learning PhD.
Okay, I feel like I saw online, it says a PhD in machine learning. So that was impressive, from Cambridge in 2019, I do believe. And I think since then, Carolina's been at Element AI.
That is correct, yes, which was acquired by ServiceNow actually recently.
Right. And you're a lead research scientist there. I think that's your designation. Okay, very good. So I've had a little bit of chance to interact with Carolina, primarily at a program at the Simons Institute, which I encourage you all to check out. It does lots of interesting machine learning programming. And I always really enjoyed her comments on various papers, you know. So yeah, I thought it was very insightful. So I think, you know, from your work, what I know are mainly the Pac-Bayes things. And I don't know if that's what you're going to talk about, but, you know, this question of how to understand generalization and how to get something sensible, which Misha's been telling us about, I think is like a perennially interesting subject. So I'm quite curious to hear your thoughts on it, and take it away if you're ready.
Thank you. Yeah, so I will talk about Pac-Bayes, and I will talk about some related work as well. So most of my work is focused on understanding why does deep learning work. And in this talk in particular, I'll be focusing on why does deep learning generalize. Now, there are, of course, a lot of, you know, exotic notions of generalization, out of distribution generalization, few-shot learning, data distribution shift, and so on. In this talk in particular, I'll be focusing on arguably the simplest notion of generalization, which is in distribution generalization. So why focus on this simplest notion? Well, there is as yet no satisfying theory explaining why our parameterized neural networks trained by variants of stochastic gradient descent generalize from training data to test data on standard benchmarks. And probably that's what Misha covered in his first few lectures. And without a solid foundation, we have little chance of understanding and taming more complex phenomena, such as out of distribution generalization. And this gap between practice and understanding is, of course, a growing liability, especially as we start integrating deep learning in high-stake applications, such as self-driving cars, healthcare, and so on. So in this talk, I'll be describing recent progress past various barriers towards explaining generalization. So let me start with a backstory, and with Zhang et al. Paper from 2016, which is well known by now. So in 2016, they published a paper showing that networks trained on standard data sets could achieve both zero training error and good test error without any explicit regularization. They also observed that networks had a very large capacity, so they could memorize random labels if trained for an extended period of time. This is, of course, problematic for, you know, such VC bounds, Rademacher bounds, and any kind of bounds that try to bound the error of a 0-1 loss class. And such bounds are actually vacuous. The reaction from many experts was, when this paper came out, and actually I was at Simons Institute then in the Foundations of Machine Learning program, was that what was obviously missing from Zhang et al.'s story was margin and the implicit regularization that SGD may bring, such as increasing the margin or you know, controlling the capacity in some other way. And this is in line with actually some older work by Neishaber et al. From 2015, where the authors had similar observations, showing that SGD's generalization error was not affected by increasing network size or lack of regularization. So in that work, I believe they train larger and larger neural networks and show that the test error actually keeps going down instead of going up. And this motivated the authors to propose what they called implicit regularization as explanation for generalization. So the likely explanation was that despite there being no explicit regularization when we train neural networks with stochastic gradient descent, SGD has some implicit regularization, perhaps controlling the norms, maximizing the margin, or controlling the capacity in some other way. And indeed, 20 years ago, Bartlett set out to explain why large neural networks generalize. And he showed that generalization error can be bounded in terms of the norms of the weights. So he derived a generalization guarantee that depended at that time on L2 norms. Now he looked at sigmoid networks in a particular norm. When it comes to Rayleigh networks that are invariant to various rescalings, L2 norm didn't quite work, and Nationber et al. In 2015, they introduced something called a PAF norm based Rademacher bound, which was custom built for Rayleigh networks, which is essentially saying that no matter what the size of your neural network is, if you rebalance the weights and you have a small norm and a large margin, then you'll have a small generalization error. So at that time, I was somewhat of an outsider, and I thought, let's go and check. Do these bounds actually explain generalization? And I think what wasn't really appreciated at the time was the empirical evaluation, or the role of empirical evaluation of theory. So do these margin bounds that depend on the norms actually explain generalization in deep learning? So I train a small neural network on MNIST dataset, a fully connected neural network, and I measured the PAF norm during training. So on the x-axis, we see the number of training epochs. On the y-axis, the PAF norm. We see that the PAF norm is growing during training, but the bound depends on the PAF norm divided by the margin. So the PAF norm can grow if the margin is also growing. Indeed, the margin is growing. But if you look at the y-axis scales, the PAF norm plot is on the log scale, and the PAF norm itself is growing a lot faster than the margin, leading to a vacuous bound. So in this top plot, in this column, the overlapping blue and orange lines are the training and test errors of this network. And the green line is the PAF norm-based generalization bound, which becomes vacuous within just a few iterations of training. Now, what if we explicitly regularize to have to control for the PAF norm, to make sure that the PAF norm is small? So if you look at the second and third columns, where I added different amounts of explicit regularization, we can see that the PAF norm grows, plateaus earlier, so as seen by the middle row plots. But unfortunately, the margin, as seen on the bottom plots, also doesn't grow as much, leading still to vacuous bounds. And only when you really increase regularization, eventually you might end up with non-vacuous bounds, but now your training and test error are 30% or whatever this is. And this was actually even binary MNIST, so it's pretty bad. And these experiments actually have been recently extended in Nagarajan and Coulter settings, showing that not only the bounds are vacuous, but even the dependencies are wrong. So we saw that empirically, the norm was not small enough relative to the margin to explain generalization. And if we want to say that, we explain generalization in deep learning, not only we need to find that, some kind of X implies generalization, such as small norm and large margins, but we also need to show that as you defines X, so as you defines, a norm that's small enough and a margin that's large enough, that will eventually lead to generalization. There are two parts of the story. So what structure can we connect to generalization, both theoretically and empirically? So if not margin and the norm, what structure is sufficient for generalization? So the idea that I had a few years back was to exploit flatness. So flatness means that non-trivial random perturbations of the weights have the same loss. So in this toy picture of the loss landscape, optimization landscape, let's say we're on stochastic gradient descent and we arrive at solution somewhere here. If we perturb these weights, we'll still have a fairly small empirical error. And these ideas actually connect back to the work from 1990s and early 2000s, which I encourage you to check out. And the references are listed here on the left. So we can actually link flatness to generalization using PAC-based bounds. So assume that the loss function is bounded and the nature chooses some data distribution D. We choose a distribution P on the weight. So here's my weight space and R to the P, a two-dimensional picture. Let's say I put a Gaussian somewhere here, which I call the prior. then we get to observe the empirical risk. So we get to observe the data, the nature samples the data, and we get to observe the empirical risk surface. In this particular case, we see two minima. One minima that's pretty flat, wide, whatever you want to call it, and another minima is quite sharp, maybe with a smaller empirical error, but much sharper. What PAC-based bounds say is that of high probability for any posterior classifiers Q, so for any randomized classifiers Q, any distributions over the weights, the generalization error of Q is bounded in terms of the KL divergence between Q, your posterior classifier, and P, your prior classifier that you got to choose. So again, in my example on the right, I could choose a prior Q, which is centered in this flat minima region, or sorry, posterior Q here, or another posterior Q prime, which is centered at the sharp minima region. Now, both of these will have roughly the same error. But what PAC-based bound tell us is that the generalization error of Q will be bounded by a much smaller quantity than of Q prime, because the KL divergence between Q and P will be much smaller than between Q prime and P. And if I wanted to decrease my KL divergence between Q prime and P, I would have to perturb Q prime quite a bit. As a result, incurring a lot of empirical risk.
So can I ask a question, yes, Carolina? So this is something, because I don't know anything really about PAC-based, that always confuses me. So it's like, you know, how do you choose the Q, or, you know, the Q prime, or whatever, you know, so the goal is somehow in your picture just to choose something that's spread, and your hope is that, like, you know, if you minimize KL divergence from something that's kind of well spread out, then maybe you're more likely to pick up the kind of like flat parts, and that's going to be good for you. Is that the?
Yeah, so it's a great question. So, you know, PAC-based bounds are valid for any choices of Q and P for as long as Q, as long as P doesn't depend on the data, though that's not entirely true, as I'll briefly mention later.
Okay.
And in this particular case, how I used PAC-based was by training a classifier using stochastic gradient descent, arriving at some weights WSGD, and then trying to fit a Gaussian as wide as possible, such that my KL would be small.
I see.
And the prior, you know, if you choose the prior naively in a data independent way and you don't have access to the data distribution, of course, it's natural to choose the prior to set at initialization. Again, a Gaussian with some variance. And the variances can be tuned using the data, and you need to account for it via union bound. You could, of course, explicitly minimize a PAC-based bound, and that would lead, you know, to a particular algorithm and particular classifier Q. And again, given P, there is an optimal choice of Q, and given Q, there is an optimal choice of P, and there are all kind of things like that. But since my goal was really to understand generalization of classifiers found by stochastic gradient descent, I just train a classifier using stochastic gradient descent, and then kind of put a Gaussian as, you know, with a high variance as possible to minimize the KL divergence.
I see. That's for Q, and then for P, you basically choose the kind of way roughly people actually initialize networks so that they're trainable and stuff. Is that the?
Yeah. So just like initialize the network, set the prior right at initialization, the prior, the mean or the prior Gaussian at initialization.
Got it.
Now, I will briefly mention in just a little bit, kind of more better choices that are data dependent.
Okay, thanks.
Okay, so what we do in this work, in our 2017 work, was that we exploited the flatness in the optimization landscape via PAC-based bounds, and by doing actually directly non-convex bound optimization to obtain non-vacuous bounds for over-parameterized neural networks. So we did the optimization, which was slightly adjusting the mean of the Gaussian and also optimizing for the variances of the prior and posterior. And how our work was really different at the time is that we focused on the empirical evaluation from the very start. But there are still quite a few weaknesses. The bounds were numerically too loose to explain observed generalization. So for MNIST, I think in a binary case, you know, where we had actual risk of 3%, our bounds were giving us 17% or so, which is not great at all for MNIST. And the bounds hold only for these perturbed classifiers, not the original classifiers that stochastic gradient descent found. And they actually didn't scale correctly. So as we increased the network, our bound got worse, mostly because our distance from initialization that the KL depends on for these choices of the prior and posterior, where the prior is set at initialization, posterior is set at the weights obtained by stochastic gradient descent, this distance was growing as we were expanding the network. So what are we missing? What are the barriers to explaining generalization? So the barriers that I would like to talk about are the following three. One is statistical, computational, and analytical. So by statistical barrier, I mean that generalization may rely on favorable properties of the data distribution, but real-world data distributions are unknown, of course. Computational barrier refers to that generalization may rely on quantities that are known but are hard to compute. An analytical barrier refers to that generalization may happen in ways that our current mathematical tools cannot capture. So maybe we don't even have the right theories for capturing generalization. So how do we overcome statistical barriers in PAC-Bayes? Well, one proposal that we had recently was using data to obtain better priors. So tight PAC-Bayes bounds depend on the data distribution, actually. So if you consider some kind of posterior distribution Q, whatever it is, data dependent, maybe I train, a GD on my data S, and I fit a Gaussian there, whatever choice I made, PAC-Bayes bounds tell us that the prior minimizing the KL term that appears in the Biden expectation is actually a distribution dependent prior P star. So P star, the optimal or oracle P star, equals the expected posterior distribution where the expectation is taken over draws of the data. But of course, we don't know the prior. Sorry, we don't know the data distribution, and the prior is actually looking at this P star, the prior is actually a prediction, right? We are trying to predict where our posterior Q will land for the given, given that it has access to this data set S. And the unknown data distribution is a statistical barrier. So there's a fundamental tension in PAC-Bayes that PAC-Bayes priors P can depend on the data distribution, right? There is an expression for the optimal prior, but it cannot depend on the sample, on the training data. But our only handle on this unknown data distribution is, of course, through the training data, through the sample S. But in fact, number one is wrong. So as we show in our recent papers, well, I mean, there's older work, first of all, of course, trying to approximate optimal these oracle distribution dependent priors through the sample. But what we more recently show is that the optimal prior can be a data dependent one, even if you know the data distribution. So I won't go through these references, but again, I encourage you to check out, or please feel free to email me if you have more questions on this. But there's a large literature on data dependent priors, either through differential privacy, as we did in our NeurIPS 2018 paper, or for stability, or for various other approaches. But what we show in our most recent work is that even if you have a data distribution, choosing the prior P star, which is this conditional expectation of the posterior, so where you condition on part of the training set as prime is a subset of S, you might be better off and you might get a better bound. So actually data and distribution dependent priors may be optimal and do better than just a distribution dependent priors. And just to give you a little more intuition, so imagine a scenario where we have decreasing learning rates during training, decreasing step sizes during training. And let's say that we initialize our prior P at initialization, which is this red thing. We train with stochastic gradient descent, we'll be maybe fitting a Gaussian somewhere here for our posterior Q. But now if we allow the prior to depend on just a few data points that the blue line, the blue trajectory access during training, then we can continue using those data points to get a much better, more informed prior. And of course, if you condition on more data, you'll match the posterior even better, on more data match even better. There's of course a limit to this. So just let me go back, actually, I forgot to copy the formula. If you look back at the PAC-Bayes generalization bound, the KL, we want a small KL, but we divide the KL by M, which is the number of our samples that the prior did not have access to, and only the posterior had access to. So the more data we give to the prior, the smaller this M becomes. And so there's, of course, a trade-off between how small you want your KL to become versus, you know, what this M becomes. Anyway, so here's just some intuition on kind of data-dependent priors, but as you said, there is a lot more to this, and feel free to reach out. I can give you some references. So up to this point, we studied Gaussian perturbations of the SGD-learned predictors. And this allowed us to capture the role of flat minima in generalization. Next, I will discuss Gaussian perturbations at every gradient update, so not only at the end of training, which will allow us to capture the role of min-match gradient covariance in generalization. Now, before I continue to this next part, I'm happy to take any questions if there are any.
So I actually have a question, another one, Carolina. So when you try to take your training set, I think you're kind of just saying you have a bunch of training data. Now, like, just take some of it, and you could just imagine training on it. And you can just see, like, you know, what do you get? And you say, well, you know, if that subset of your training set is kind of more or less representative, at least at some level, of the whole thing, maybe that's not a bad prior. That's kind of what you're saying.
Yeah, so that's definitely kind of what I'm saying. I think there are two, though, kind of little details that I did not mention. One is that your posterior still has access to all of the data. So that doesn't change at all. So even if you use some of the data for the prior, the posterior doesn't change. It can still depend on all of the data.
Okay.
And so it's not like you're taking away data from your posterior when you're trying to get a better prior. And another thing is that it's actually exactly what you said. So through experiments, which I did not show here, but we show in our paper, AStats this year paper, is that even if you have the data distribution, just maybe taking, I don't know, 50, 80, depends what you want, % of your training set might be just as good as using the data distribution or the data distribution in a few data points. So of course, it's very data distribution dependent, but as you said, the hope is that for nice data distributions, if I allow myself to look at some of the training data, I will be able to actually get a pretty good sense of what my data distribution is like and predict where my posterior will land. And maybe the third small thing to mention is that even if I knew the data distribution, so forget that, these few samples might approximate my data distribution well. So even if I had access to the data distribution, if I have, for example, decreasing learning rates in mini batches, and through my first iterations of training, I happened to look at some really weird data points that send me to some really weird direction in a non-convex setting, I can only recover from my prior where my posterior will go if I allow myself to view these first few samples where it took massive steps in some weird direction. Does that kind of make sense? So
yeah, definitely.
That's really kind of what this informally stated theorem here. We prove it in the paper by an example like this, where we construct an example with SGD with decreasing step sizes and show that even if you have a data distribution, having access to the actual data during training, during the first iterations of training, may give you a huge advantage and turn your bound from vacuous to non-vacuous.
Yeah, I see. I understand. You're kind of saying, like, you just in the first couple steps either go left or go right, and you just need to know which one you do. Otherwise, you're just equally likely to be everywhere, and it's all kind of useless too.
Yeah, that's exactly right.
Thank you. Appreciate it.
Thanks.
Sorry, I have a question. Hi. So does the data-dependent prior also depend on the training algorithm or the neural network itself? Because you are using the network to get to Q of S or P of S, right? So it depends on the training algorithm as well, right?
Yeah. So if Q uses a particular training algorithm, the optimal P star would be expected Q, which of course will take the algorithm into account. In practice, of course, I wouldn't see necessarily that doing also a SGD with the same mini-batch size on part of your data is the optimal thing to do, but it's a thing to do. And we couldn't find anything kind of more clever through even like various, more complex versions of optimal transport that would work. But yeah, that's a great question.
Thank you.
Okay, so let me move on to the next part. So in this part, as I mentioned in the previous slide, we'll be perturbing with the Gaussian our updates every iteration. And this corresponds to, if you had Gaussian perturbation scaled in various ways, it corresponds to various smooth versions of stochastic gradient descent, private versions and so on. And if you choose particular learning rate eta and particular scale inverse temperature parameter beta, you'll actually have stochastic gradient longevity dynamics. So just for this talk, though, all of this is extendable for different versions of eta and beta, I'll be kind of referring to SGLD, stochastic gradient longevity dynamics. So SGLD, every update of the weights adds this Gaussian noise term where epsilon is sampled from a Gaussian. And this additional noise term makes SGLD much easier actually to analyze compared to stochastic gradient descent. And the inverse temperature parameter beta that I mentioned, it trades off exploration versus optimization. So in this one-dimensional example on the right, in the right corner, imagine that you started the cross, so you initialize your SGLD run here, and you run training. If you were running SGD, or full batch gradient descent, you will probably end up in this minima here. Just go down here. But if you run SGLD-VIF, depending on the noise term epsilon on the inverse temperature parameter beta, you will probably be sampling quite a bit here, then maybe you're returning here, and so on. So there are two views of SGLD. One is that SGLD samples from a Gibbs distribution, which has density proportional to exponentiated and rescaled optimization objective F, let's see, whatever it is, some kind of loss function. But this only happens under unrealistic assumptions. Another view is that SGLD optimizes, and the resulting weights that you optimize, they don't carry too much information about the data S. So just by adding these perturbations, you're kind of not leaving too much information about S if you don't train for too long. So the question that I'm asking here is, does this latter view of optimization explain generalization of SGLD?
Sorry, Carolina, just very quickly, what do you have in mind by unrealistic? I'm just not exactly sure.
Yeah, it just unrealistic because you need to run it for a very long time. Yeah, and it actually in practice, you don't, and you end up just being stuck in one minima instead of actually sampling from this Gibbs distribution.
I see. You're saying the tunneling time is like exponential in the kind of barrier size. And so, okay, gotcha. Thank you.
So let me introduce now information theoretic generalization bounds, which we'll be using kind of to study generalization of SGLD and analyze the information leaked by the weights about the data. So let S denote the training data sampled ID from some data distribution D, and W the learned weights that are learned by running some algorithm, which is SGLD in this case, on the data set S with some additional randomness U. So such as mini-batch order, this Gaussian noise that we're adding, and so on. To find the expected generalization error, EGE, of the classifier parameterized by W and the data for data set S as the expected difference between risk and empirical risk of your classifier, and assume that the loss is bounded in 0, 1. Then Zhu and Roginski a few years back showed that expected generalization error is bounded in terms of the mutual information between the weights and the data. So what I'll be kind of trying to get to in the next few slides and asking is, does this theorem explain generalization of SGLD? Okay, so can we explain the generalization of SGLD through small mutual information term between the data and the weights? Now there are again barriers. One is statistical barrier. So this mutual information term depends on the unknown data distribution. And by the way, for those more familiar with Keil divergences, I'll be defining mutual information terms of Keil divergence just in a minute. And another barrier is computational. So even if the data distribution were known, the mutual information term is actually still intractable because we can't really explicitly write down the distribution of on the weights induced by SGLD or SGD or whatever. So let me first address the computational barrier, which is saying that even if the data distribution were known, this mutual information term would be intractable. Let ST denote the mini-batch sampled at time t from our training set S. Then Pensa, Zhao, and Low observed that the chain rule on mutual information implies that the mutual information between the data and the weights at the end of training is bounded in terms of the mutual information between the data and the whole trajectory W0 to WT, which can in turn be split into the sum over training time of these stepwise mutual informations between the data accessed at training time t-1 and the weights that we have at WT conditioned on the previous trajectory, what we've already seen. Okay, so in words, the information leaked about the data by the final weights can be bounded above in terms of the sum of information leaked about mini batches at each training time step t. Then the next hurdle is to still bound this stepwise mutual information, which is still unknown and intractable. So we still have statistical and computational barriers. And the insight that we'll be using is that this one-step mutual information term is actually optimal expected loss in the following prediction game. So imagine that you observe the trajectory of SGLD from time 0 up to time t. And your goal is to estimate distribution on the weights Q on the next step weights, given this trajectory and given the data accessed at time t. And if your prediction is some kind of distribution P on these weights, then you pay a loss, which is scale divergence between Q and P. Then the optimal strategy is to predict P star, which is expected, again, posterior distribution Q conditioned on the trajectory to time t, which actually gives us the expected loss, which is just the mutual information. So now you can see how mutual information relates to scale divergence. So expected scale divergence for this optimal prior P star, actually the same that I mentioned a few slides back when talking about PEG-based, equals to the mutual information between the mini-batch at time t, the weights, and the condition on the trajectory. So this one-step mutual information. Okay, so in this prediction game, this is the loss that I would be paying, and this is my optimal strategy P star. But of course, P star requires us to know the data distribution. One thing to note, though, is that every prediction scheme P yields an upper bound on mutual information. So we can choose any P we like, and we'll be getting an upper bound on our expected loss. Don't forget that stochastic gradient longitudinal dynamics, you add Gaussian noise every step, which makes the expression of Q, so the distribution on the weights, next set weights given my trajectory, very simple. It's just a Gaussian with the noise that depends on the noise that we added here to the gradient step, and center it at the weights that are now previous weights updated based on the gradient of our objective, which of course consumes information about our mini-batch ST. Now, however, in this game, I'm not given the mini-batch ST, so I cannot choose a prior that depends on ST. And what Pensa, Zhao, and Low do in their work is the following. So as I mentioned earlier, they bound the mutual information in terms of this sum of stepwise mutual informations, and they play exactly the same game that I described, where they observe the trajectory at the time t. They need to predict, they want to predict this distribution Q on the weights that depend on the mini-batch, which they did not get to observe. So they choose to predict P, which is a Gaussian, but centered at where I am right now, right this moment, because they don't have access to ST. And they'll be paying a loss. It's a scale divergence between Q and P. It's easy to compute. It will be, since the variances are the same, it will be just the difference between the means. So it will be the size of the gradient essentially, which we bound using Lipschitz constants. So at the end, you get a bound, which is saying that expected generalization error is bounded in terms of the sum of these, the sum over training time of these learning rate, temperature parameter, inverse temperature parameter, and Lipschitz constant. Now, the limitation of this bound is that we must predict where in our trajectory will go at the next time step, given where we are right now, but we have access to no data. And that's where data dependence will come in again. We can use conditional mutual information, conditioning on all but one data point. So imagine a game, a modified game, where not only we observe the trajectory up to time t, but we also get to observe all but one data point. So we're missing the JAVE data point. Just as before, we want to estimate the same Q, which is a Gaussian. But now we can make the following prediction. If our mini batch does not contain the missing data point, the SJAVE data point, then we can actually predict Q. We have access to all the information we need to actually choose Q. If ST, however, contains the missing data point, we can still make a better prediction by using all the data we have access to, except for this JAVE data point that we're missing. And we'll be paying a loss, which again is the KL divergence. If we predict Q on the cases where we have access to the data, the KL will be 0. In other cases, we'll be paying a penalty, which will depend on the difference between the gradient on all of your data versus the gradient on all data except for this missing JAVE data point that we don't have access to. And we refer to this term as gradient incoherence. So if you go and evaluate these bounds again, these are experiments on MNIST, FAST, MNIST, and CIFAR. We observe the following. So the gradient norms, which are the blue curves above, they don't vanish during training. So previous bounds, they depend on the norms and they're summing the norms throughout training, they'll suffer from this. These centered norms, the gradient coherence term actually goes down with training. This is true for MNIST, FAST, MNIST, but not CIFAR 10. So we're still missing something. And if we compare to other, at that time, state-of-the-art bounds, depending on the norms of the gradients, again, we see that we do much better. So our bound is this red and blue curve. The previous bounds are these two top lines. And we are choosing different step sizes, different inverse temperature parameters. And we see that we do a lot better when we, with this gradient incoherence term. However, our bands are still growing. And so we're missing something. So the limitation of this work that I just described using conditioning on all but one data point was that there was no control over which data point was missing. So assume the following. Assume that our training set is either S prime or S double prime with equal probability, where S prime and S double prime differ by only a single data point. Now we can condition on the union of S prime and S double prime. And this is actually building on very recent work by Stanka and Zakintanu on conditional mutual information, which again, I encourage you to check out. It's really cool work. So now we can rephrase our prediction game. So in this prediction game, we get to observe the trajectory up to time t, again, just as before. But now instead of observing all but one training points, I will observe the super sample, S prime and S double prime. So I'll observe basically all of my training data except for one location where I will not know which one of the two data points belong to my training set. Just as before, we want to estimate the same Q. Now, a small detail here is that we actually have full batch setting. So I don't have the index T anymore, it's just S. And we can make a prediction P, which with some probability will be predicting a Gaussian that's taking a gradient step on the data S prime. And with 1 minus that probability, we'll be predicting a Gaussian that's taking a gradient step on S double prime. Now, if I have no information about which of S prime versus S double prime are in my training set, of course, I have to choose theta, which equals a half. I have no information. But don't forget that in this game, we get to observe everything up to time t. And of course, the past iterates provide evidence on which of S prime or S double prime is our training set. So formally, we have a binary hypothesis test, and theta is chosen based on conditional distribution of missing data points identity. And I won't go into too much detail, but like the previous bound that I showed you where we leave out one data point is the green one, the new bound is blue. And you can see that while there's maybe not too much of a difference for MNIST and only like deep into training, we see a difference. when we look at CFR, train on CNN, our old bound explodes versus this one plateaus and doesn't go as much. Now, of course, the scales are still off. So I see that I'm running out of time, so I won't actually get into kind of the last little section, but I'll quickly summarize and then go to conclusions. So what we've seen so far is that in the very beginning, we exploited flatness by adding noise to the final weights and use PEG-base. We can exploit gradient coherence by perturbing iterates every iteration of training. That was a GLD analysis. And in both cases, we use data-dependent priors to reduce impact of initial unstable optimization of not knowing the data distribution. And in the work that I just presented, we use conditional mutual information to reduce the impact of measuring information lead by the entire optimization trajectory. Now, the important thing here is that we've actually bounded generalization error of various perturbations of SGD, so not SGD itself. It's not the same. And in fact, Nagaraj and Coulter maybe kind of points out a bigger issue that perhaps you can't really analyze directly SGD. So how can we bridge this gap? So I won't go for this anymore, but again, I encourage you to check out our recent work on called In Defense of Uniform Convergence, where we introduced surrogate analysis that allows us to explain generalization of predictors that belong to a class where uniform convergence does not hold. And also work by Nagarajan and Coulter from 2019 on uniform convergence may be enabled to explain generalization, I believe. So I'm skipping over this stuff and just going directly to the conclusion slide. So we've discussed that generalization bounds for two classes of surrogates. Actually, let me skip this as well. Here. So good generalization is the product of favorable properties of course, the data, the algorithm we use, and the interaction between the two. So the bounds, type bounds or explanatory bounds, whatever you want to call them and define them, the bounds had to depend on the training samples and the data distribution. I also believe that empirical evaluation of the generalization bounds and measures is critical. The complexity terms that appear in the bounds are usually data dependent, and empirical evaluation is the only way to know how they grow, where the bounds may fail, and where we need to improve to make progress. Capturing data distribution dependence by using training samples allows us to circumvent statistical and computational barriers when evaluating theories. All right, so we can always generate more data, pretend we have more data, which will allow us to at least better understand the limitation as not knowing the data distribution. Or maybe we can use some of the samples to, again, hold out and approximate data distribution dependence, or where the trajectories will go. And instead of bounding the generalization error uniformly over a hypothesis class containing the predictor, we should think about related predictors, so-called surrogates, that may belong to a class where uniform convergence holds. So this is the bit where I couldn't quite cover, but that's also very important. And again, please reach out if you want more references. We have made progress on studying some surrogates. So by perturbing the classifiers we learned by SGD at the end of training or doing stepwise perturbations. But of course, there's still a lot of work to be done. And the bounds are, there's still progress to make understanding these surrogates and proposing the right surrogates, but also connecting the surrogates to the original classifier that we wanted to study. That's it. Thank you very much.
Okay, thanks very much. It's a very complicated world to make sense of all of these generalization bounds. And seriously, it's hard. So we appreciate your efforts in helping us do that. Because we're a little bit short on time, I suggest if students have questions for Carolina, just reach out to her directly. Presumably she'll respond to an email. I know that's very old fashioned, but still, or by chat or however people talk these days. I'm not really sure. So yeah, excellent. So Greg is going to give us the next talk. Let's see if we can get the screen share working, and then I'll briefly introduce him. Okay, excellent.
You see my screen?
Nice. Yeah, we can see your screen and we can even hear you. So
sick.
So we're doing well. Okay, so the last speaker of our illustrious symposium is Greg Yang. So very brief introduction. Greg was an undergrad in math at Harvard. I think you finished in 2017. Is that right, Greg?
Yeah, that's right.
That's right. And now he's I think technically you're a researcher at Microsoft. Is that right? That's the nomenclature you guys use at Microsoft Research. So Greg has been working quite a bit on studying wide neural networks in various contexts. He's been developing things like tensor program approaches and so on. And so, I'm excited for the talk. I'm sure we'll learn all kinds of cool things about the infinite width limit, but interestingly, kind of not in the kernel regime, or not necessarily in the kernel regime that we've been hearing a lot about. I think it's sort of like an interesting and important, alternative infinite width limit. So assuming I didn't get anything too horribly wrong, why don't you tell us about it, Greg?
Yeah, awesome. Thanks a lot, Boris, for this opportunity. Thanks everyone for coming today. I see we have a good crowd here. So let me just dive straight into it. Let's see. Great. So something is rotten in the state of deep learning, Hamlet once said. And in particular, I think this particular statement is a bit weird, which the statement says wide neural networks are linear models. And I'm sure you probably heard about, some of this in your course so far. How many of you guys believe in the statement? You want to raise your hands? I mean, I won't like.
Can I half raise my hand? I sometimes believe this statement.
Who vehemently rejects the statement? Nobody? No brave soul? All right, I'll be the one to reject the statement. I think this statement is totally rotten. The issue here is that I think most of the literature has focused on analyzing initialization or around the initialization of neural networks. And in particular, this is because we have enough independence to make the math really, really simple in this case. But it leads to the wrong conclusion when we start training and venture really far away from initialization. And I'll talk about two instances of this. One is the NTK parameterization in theory, and the other one is the standard parameterization in practice, where by standard parameterization, I mean like what you use by default in PyTorch. So let's start with the problems with the NTK. Hopefully you guys have learned something about it so far in your courses. But just to briefly review, the neural tangent kernel, I mean, the basic idea is very simple, right? Like neural networks a priori are very hard to really understand because of nonlinear interactions between different components. So, as any, say physicists do, you just first try to tackle this by Taylor expanding some way. And here we're Taylor expanding around the initial parameters. So we end up saying that the change in the function due to change in the parameters is roughly equal to the gradient initialization times the change in parameters. So you can rearrange this equation using gradient descent, the definition gradient descent, to rewrite this into a functional equation that the change in function is equal to some kernel times the loss derivative of that function at that time. And this kernel is just given by the inner product between gradients of different input points. And the remarkable thing, of course, with this line of work is that as width goes to infinity, this approximation, this naive Taylor expansion becomes exact in the infinite width limit in a so-called NTK parameterization, in a particular parameterization. And this GIF is just showing that the landscape becomes convex, more and more convex in this parameterization as width becomes large. And this is very nice, right? Because now you have a essentially linear equation if you have square laws, for example. So it's very easy to analyze how the function evolves in this large width limit, and it gives you optimization generalization results that just weren't accessible before about neural networks. But the problem with this is that the feature kernel of such a network in such a regime does not evolve. So pre-training, like what you see in BERT GPT or like large image models, is completely useless in this regime. And just to be concrete, what do I mean by pre-training and transfer learning? So like if you have I don't know if you guys train any models yourselves, but like for example, the ImageNet revolution, training large ResNets on ImageNet, and then downstream fine tuning for like object detection or segmentation. That's one instance of pre-training and transfer learning. Another one is more recent, like BERT, GPT-3, large language models, right? Like we pre-train a lot of language data, and then you can use it downstream for other tasks like sentiment analysis or something. So again, I want to like hammer home the point that like pre-training is useless in the NTK regime. So it kind of like that's like one of the most important aspects of modern day deep learning. And I'm going to be very concrete. Like here's how to waste your money with NTK. Suppose you're OpenAI and you like got money from investors, like probably I don't know, couple well they got like a 1 billion from Microsoft. But suppose you allocate like 10 million for like GPT-4. Okay, you want to train GPT-4. I'm allocating $10 million to this. And suppose like you heard about the NTK regime, so you think it's probably a good idea, right? Because like all the rage about NTK these days, right? So it's probably a good idea to train NTK GPT-4. So you start again by training on like large language data, a large amount of language data, and then after training you want to fine tune it on like for example codecs like the GitHub Copilot OpenAI codecs. You want to fine tune it on code data to get a performance boost. And how do we do this kind of fine tuning? So typically you discard the readout layer from pre-training because the pre-training and fine-tuning objectives are just different. And during so there are two kinds of fine-tuning here. So one is linear fine-tuning, it's the easiest thing, which is just training just the last layer. And what happens is that if you do this, then in the NTK regime, because your feature kernel does not evolve from initialization during pre-training, you might as well have just started from scratch for linear fine-tuning, like as in just like the pre-training has no effect at all compared to just randomly initializing a large transformer. So okay, that was no-go. The other way to do fine-tuning is you can train the entire network. But here, in fact, our conclusion will apply as well for a really wide neural network. But the reasoning is a bit more sophisticated than just this kind of like easy, nice linear intuition. So yeah, so if you have $10 million, instead of doing this, you can probably just buy GameStop or something and get better returns. So here's a concrete example of the lack of feature learning in the NTK regime, if you're not convinced so far. So here we're taking the example of Word2Vec. So Word2Vec is an early example of large-scale language pre-training in deep learning. And here you want to learn embeddings, vector embeddings of words such that semantically close embeddings correspond to geometrically close vectors. And I mean, I won't go into details about how the training was done, but so we train them, and you can in fact train the NTK version of it, and also the feature learning limit version of it, which I'll introduce later. But this is the proposal that I'll talk about. And I just want to point out that in the middle plot, for example, we're here actually. Oh, sorry. In all three plots, we're looking at PCA projections of two kinds of word embeddings. Like so they just correspond to like US cities and US states. So just two groups of word embeddings. And in the middle plot and the right plot, you can see that the embeddings are kind of naturally separated into their own clusters. But in the NTK plot, they're all kind of mixed up together, right? So like there isn't a natural separation as you see in the other plots. So this suggests that NTK just did not learn really any kind of semantics in the course of pre-training, whereas the finite model did, and also the infinite width feature learning model also did. And of course, we can also look at concrete numbers if you believe that that was cherry picked. So Word2Vec is usually evaluated downstream on tasks like the word analogy task. So this is the kind of tasks that ask the famous questions like what to a queen is a man to a woman. And the way you answer it is just like by taking the let's see, embedding of man minus embedding a woman plus embedding queen, and then you look at which word is like has the embedding closest to what you have. So on the right, I have the plot of the performance on word2vec downstream, this word analogy downstream task over the course of training. So over the course of training, we're taking like checkpoints from our progress, and then we're evaluating on the task. And we have a bunch of different curves here. The solid curves correspond to finite width neural networks. And the darker colors indicate wider neural networks. The top dashed line, black dashed line, corresponds to the feature learning limit that I'll talk about. And finally, the dot dash purple line in the bottom corresponds to the NTK or GP limit. And as plainly seen here, the NTK limit has trivial performance. Like the performance like essentially 0. And that's just because you just didn't learn anything during pre-training. So like when you do this kind of linear combination to answer the word analogy task, you're just essentially it's still all random answers. And because the vocabulary size is so large, like randomly guessing is pretty much close to 0% accuracy. So that's one point. And the second point I want to point out is that if you look at the finite width neural network curves, so the solid curves, right, you can see that as width increases, or as a color darkens, the performance increases uniformly across all times. And but also like the infinite width feature learning limit is an upper bound for all of these models, right? So this suggests that in our model, our feature learning limit is capturing the right thing. Like you're seeing this, like wider does give you better performance, right? Versus, if you think about, if you were to believe the NTK is the right limit, then your performance would go up, but then eventually come down to 0, which is a very, very strange thing.
Let me ask you a quick question about this,
Sure.
Greg. So
Yeah.
when you make these finite width plots,
yep.
What initialization scheme are you using?
Yeah, so this is using the mu parameterization I'll talk about, but essentially there isn't, so like the only difference you would see if you use like the standard initialization that is default in the original repo, it's just like in the beginning the performance will be like a bit worse, but then eventually it becomes the same. So like if you train long enough, then it doesn't matter so much.
I see. So a part of your claim, just jumping ahead for a second, is that at least in some experiments, it seems like if you take the default initialization and you train for a long time, your claim is that it is as if you had started with this other parameterization from the start. That's your claim?
Kind of, but in fact, I'll be claiming something stronger. Like you, in some sense, you'll always do better if you use our parameterization. And
I see. Yeah, right. No, right. I understand you're saying that, but I was asking about okay. So it now makes sense to me why those curves go up, because they are approximating the upper curve in some sense.
Yep.
Like you're really taking the same kind of initialization and scaling it up.
Yep.
Okay, I understand. Thank you. I appreciate that.
Yep. Great. And we also have results on meta learning. So another task where feature learning is really crucial. But I won't describe it here, but essentially the takeaway is exactly the same as what we have on word2vec. So, this essentially ends my description of why NTK sucks and we should move beyond it. And Yashio agrees with me. He says that NTK doesn't exhibit a critical element of deep learning, which is the ability to learn increasingly abstract features as we train. And he agrees that our work takes an important step toward a theory that captures this capability in overparameterized neural networks. Okay, now let's look at what's the deal with standard parameterization. What are the problems with it? So again, the standard parameterization is just what people use in practice, like the default given in PyTorch. So one problem is that the hyperparameters, the optimal hyperparameters are unstable in standard parameterization. So so in both of these plots, we are parameterizing the neural network in standard parameterization on the left, or our proposed parameterization on the right. And we, for each width, going from 256 to 8192, indicated by different colors here, we sweep the learning rate and we train it for until convergence, or 20 epochs, which is pretty close to convergence. And we plot the training loss curve on the same plots. So on the left, you see that as we increase the width, which corresponds to the color darkening, you see the optimal learning rate, right, starts from 2 to the -6 here, and then as width becomes larger, it shrinks and shrinks to like, I don't know, around 2 to the -9 here. So the optimal learning rate is very unstable, and in fact, if you use the optimal learning rate for 256, you'll kind of like do really badly when you scale up to 8192. But this is not the same with our proposed parameterization. You can see like the optimal learning rate is pretty much just constant. Like you don't, if you tune the small learning rate, small network learning rate, you can just use the same one for the large neural networks. Okay, so that's one issue with the standard parameterization. Another related issue is that different activations or pre-activations will blow up in standard parameterization as you scale up. So here, I very concretely demonstrate this in the transformer model. By the way, like the previous experiment also like works for a transformer or like resonant, whatever have you. MLP is just the simplest case. But here I want to be a bit more realistic and say that like different activations or pre-activations in different parts of the network can blow up. So here we're looking at transformers, and in each plot, I'm plotting the change in the activation of like the lodges or the attention lodges or the input word embeddings, so different parts of the neural network, the change from initialization due to training. And the way we measure this change is by taking the standard deviation of the change over the neurons, over the width dimension. The different colors indicate different time steps during training. So here we're just taking 4 steps of training. And the point here is that, right, as you train more, which indicates the darker colors, your lodges or the output network will blow up as width increases. Right. Same thing with the attention lodges, which are the lodges going to your self-attention softmax, but not the input word embeddings in the standard parameterization. So the top row is standard parameterization. But if you look at the bottom row, which corresponds to our parameterization, it's all very, very stable with width. So there's no such problem. And the reason I'm showing, 3 different parts of the neural network, and I'm showing that the input word embedding is stable, whereas like the lodges, attention lodges are not, is because, some of you might say, okay, the lodges blow up easy, right? Just lower the learning rate, then you're okay. But the problem is if you lower the learning rate for lodges, then the word embeddings in the input layer does not, it will learn less and less as width goes to infinity, and you will just get stuck in initialization when width is exactly infinity, right? So like different parts of the network is like learning at different speeds, and you cannot, if you just tune the learning rate, the global learning rate, you cannot appease them simultaneously. But our parameterization by design is able to do that. And Ilya agrees with me that like this property that stability hyperparameters and also making sure all layers learn exactly the same order during training is extremely exciting and has a potential to change the way that the field thinks about large model training. So what's the deal with standard parameterization? Like, what's wrong with it? And the root of the rot is that the original derivation for standard parameterization essentially just considered initialization, but did not consider beyond initialization. Of course, the fact is that the weights correlate after one step of SGD. So you really need to like take that into account. Okay, so I'll pause here. Any questions so far?
So
Okay.
I have kind of a meta question for,
Sure.
I think you're about to get to this, which is why I wasn't asking it.
Yeah.
Like, I don't think we've necessarily seen the, like, in the school yet what the difference is literally between like standard and NTK parameterization, for example, and just these words. But I assume like at some point very soon, you're gonna like write down some formulas with, you know, W and eta and, you know.
Kind of. I guess I'm skipping a little bit over the basics, but I can write it down.
Yeah, maybe if it's not a hard thing, just like, you know, just even half a like a 1 minute thing, just so people know, because I think people know just but by different words potentially.
Yeah. Okay, so the thing I'm afraid of is that like PowerPoint sometimes crashes if I ink on the slides. So I don't know if I want to take that risk. But how about like let me just describe what standard parameterization is, maybe with words, and then I can, yeah, I don't want to like have to like restart the slides. So standard parameterization just means like, you know, you are initializing each weight matrix with variance 1 over fan in of the neural network of the weights. So like the dimension coming into that layer is used as a denominator of the variance of the random initialization. So that's the standard parameterization. The NTK parameterization is very similar. It just instead of initializing randomly sampling the weights with this variance, you instead sample each weight with standard Gaussian, so variance 1, but you pull out this initialization scale to a explicit multiplier. So you sample each weight as standard Gaussian, but then you multiply explicitly by 1 over square root of fan in. And so in the forward pass, like it's exactly the same, but just in the backward pass, like there's some effect on the scale of the gradient. So I'll talk a little bit about this, not exactly on the way you actually parameterize, but like on the effect on the operator norm of the gradient and so on. Okay, so now the question is, you know, what's the right parameterization if NTK parameterization and standard parameterization are both sucky, right? What's the right one to consider? So for this, we really need to venture out of the comfort zone of initialization, where, you know, the object of concern is like W0, which is the initial weights. And we need to venture into the unfamiliar territory of training, where the object of concern is delta W, the weight updates over the course of training. And these weight updates are sums of outer products, right? Like if you just look at how back propagation works, the outer products are between like gradients coming back and incoming activations into each layer. So whereas the scale of initialization is controlled by the standard deviation of sampling, the scale of the weight updates are controlled by learning rate. And the central question to ask is, how do you set the standard deviation and the learning rate? So we can try to write down some considerations for what consists of a good parameterization. And for example, we can require that anytime during training or initialization, every activation vector should have constant size coordinates, where this here data 1 means like not dependent on width. And this includes input output dimensions are considered constant with respect to width. All right, so, you know, why should we consider this? You know, as seen before with the standard parameterization plots, you don't want your activation vectors to blow up, right? Because or shrink to 0, because you will go out of the floating point range, right? If you blow up, you get nans. If you shrink to 0, like you essentially don't get any gradients. So you want constant size coordinates. For a similar consideration, the network output should also be constant size, though it can be zero. Like output can be zero. That's fine. Finally, all parameters should be updated as much as possible without leading to divergence. So this kind of corresponds to practitioners' intuition that you should use like as large a learning rate as possible, so you train faster, and usually generalize better as well. And as we'll see, this also leads to feature learning in our case in the infinite width limit. Okay, so the key claim is that there is a unique parameterization which we call the maximum update parameterization that we abbreviate as μp, satisfying the desiderata given above. And this unique parameterization is given by any of the following 4 equivalent conditions. Okay, so what are the 4 equivalent conditions? One, we can look at the operator norm. And this table says that the W0 and delta W should have operator norms scaling like the values in the table where everything here is theta in big O notation. So we're suppressing constants not dependent on width n. And since there will be a lot of numbers on this page, I want you to focus on the pink cells. So in here, I want you to focus your attention on the fact that we require W0 and W to have to have operator norm in the hidden layers. So these matrices will have n by n dimension. Okay. All right. So again, the operator norm of the hidden weights W0 and delta W should be order 1. Equivalently, we can also look at Frobenius norm, and we require that W0 have Frobenius norm square root n in the middle layers, and delta W to have Frobenius norm order 1 in the middle layers. Equivalently, we can also look at the coordinate size of these matrices. And in the middle, the hidden layers, we want W0 to have 1 over square root n coordinate size, and delta W to have 1 over n coordinate size. And finally, equivalently, we can also look at the hyperparameters, which is how you'd actually implement this. And here, I don't want you to focus on hidden layers, but rather on the output layers where the obvious is more different. The difference is more obvious, where we require standard deviation of the initialization and the learning rate to be both 1 over n. Okay. All right. So this is a lot of numbers to take in. So let's breathe a little bit and digest this by comparing against some common but faulty intuitions for how do you scale these quantities. So one intuition regarding Frobenius norm is that the Frobenius norms of W0 and delta W should be on the same order. And this is inherent in the design of Adaptfactor and LAM optimizers, which are some like the optimizers people use in practice. But as you can see, this contrasts with the Frobenius norm table here, where we have square root n for W0 and 1 for delta W, right? So if you were to make delta W the same Frobenius norm as W0, so this cell will be square root n instead of 1, and in that case, your network will actually blow up as width goes to infinity. So this is actually bad. You don't want to train your large model with this intuition. Another intuition regarding the coordinate size is that the delta W, again, like the update to the weights over the course of training, should have constant size coordinates. For example, this is inherent in the design of Atom, or say like 1 over square root n, like the initialization W0. But again, like these coordinates are too large compared to the table here, where we have 1 over n for delta W. And this will actually also blow up as you train a large model. Finally, we have a common intuition that we initialize each layer with 1 over fan-in variance, like what I said earlier about standard parameterization. And we typically, we typically use a constant learning rate for all layers, right? And this is different from this table where we say that both the standard deviation and learning rate should be 1 over n. Okay, so So this summarizes, the key claim here, and hopefully this description digest a little bit of the information for you. But let me know if you have any questions.
I have a quick question, sorry. Just for clarification's sake, can you say what the change would be in the fourth table, the hyperparameters table, for either standard parameterization or NTK?
Sorry, can you repeat that question? Like the audio was a bit weird.
Oh, sorry. So I was asking if you can repeat, say, for the fourth table, the hyperparameters table, for either standard parameterization or NTK. Like, what would be different here?
Can you wait a little bit? I have it in a later slides, but I won't get to it. Yeah, I won't get to it just now, but yeah, just wait a little bit and then we'll get to it. Cool. Any other questions? All right. Oh, Cheng.
Yeah. Can I have a question here? So just to be sure I understand it correctly. So for NTK initialization, for the infinite wide neural network, it is a linearized model, but for standard parameterization, it's not. It's just a feature learning, right?
Oh, so what happens with standard parameterization is that
I'm sorry.
Is as your width becomes very large, your model training standard parameterization will blow up. So it's not stable, and
so
to make it not blow up.
So it is not linearized model, right?
So let me finish. So you will blow up as your width becomes very large, and in order to make it not blow up, you need to use a smaller learning rate, and the largest learning rate you can use for standard parameterization will make it be in the kernel region.
But if the learning rate is small enough, I mean, it's sufficiently small, will it still blow up?
You will not blow up, but you will be in the kernel region.
Oh, okay, still a kernel. Okay, I see.
So you're choosing between blow up or kernel region. Like there's no feature learning. I mean, like I guess that if you have like, really large like floating point range, for finite width neural networks, you can of course do feature learning. For finite width neural networks, of course you can do feature learning. But the question, of course, is like when the width becomes very, very large, like what is the resulting behavior? And I'm saying that standard parameterization does not play well with a very large neural network. You're choosing between blowing up or kernel dynamics.
Okay, I see. Thank you so much.
Okay. All right. So